Welcome, everybody. My name is Edward Lee. I'm from Berkeley, and just a couple of logistical things. We are going to be recording this. We will make the recording available, as well as all materials that we have available. Let me share my screen and just give you a little bit of orientation here. So there is a web page that has the collected material for this tutorial. You can see the URL right here. And what we're going to do is we're going to start out with just an orientation into how to get started with the software, and then walk you through building simple examples and then basic concepts. And then we'll dive in more deeply and talk about concurrency and performance, and then give you an overview of the ongoing research. We ask you to mute. If you aren't muted, someone is not muted, unless you're speaking. And also to please feel free to use the chat to raise questions at any time. So we have several people who are collaborating on this presentation, and will be, whoever is not speaking will be monitoring the chat. So this webpage that is pointed to here has an outline of the program as we will follow it, with some estimated times. We're going to have various pauses throughout that are labeled 5-minute Q&A. And at that point, you can feel free to turn on your camera, and we'll try to remember to just pause the recording during those. But you can ask questions at any time with the chat, okay? These will also be perhaps a good opportunity to go get a cup of coffee or something. So let me just start very briefly by giving you a little bit of background on this project that we're going to talk about. So let me, oh yes, one more point, logistical point that I wanted to make. We also have a discussion page here that you can use both during the tutorial and at arbitrary times after the fact, that might be useful for contacting the project developers. Okay, so let me stop sharing my screen and go back to just the video presentation, okay? So just a little bit of background about this project. So the project that we're going to be talking about started in the fall of 2018, when Chris Gill from the Washington University at St. Louis and Marten from the Technical University of Denmark happened to be visiting my group in Berkeley. And they were both coincidentally very interested in programming processors for deeply embedded applications that had very predictable timing properties. And we started brainstorming about what it would take to have a modern programming framework for that was sophisticated about concurrency and time, and started sketching out a language that was very much informed by prior work we had done in a project that we called Accessors, which was part of the Ptolemy 2 effort. And Marten Lohstroh, who was a PhD student of mine at the time and is now a postdoc and will be one of the lead presenters today, had some very interesting ideas about generalizing the model of computation behind Accessors, and how and we started to understand that this model of computation was very related to, in some ways it was drawing kind of the best of synchronous languages and discrete event systems and actors. And so we got kind of excited about the idea, and Marten went off and within 2 days had built a very simple prototype compiler, and that got us kind of off the white page problem and got us starting to work on it. I went shortly thereafter to Dagstuhl and met up with a former student, Johan Ecker, former postdoc in my group, actually. And Johan, who is at Ericsson, suggested to me that we take a look at Xtext because of the infrastructure that it provides for very quickly building compilers. And so I started playing around with it and created a second version of the compiler using Xtext. And then we started to really run with that. Around that time, Marten connected up with Christian Menard at the Technical University of Dresden, who was a PhD student who was working on trying to solve problems with adaptive autosar. And he had come up with a model computation that was very closely related to what we were doing. And so we kind of roped him into this project, and he became a really powerful force behind the development. In the fall of 2019, we then coincidentally went to Southampton in England to the Forum on Design Languages, the FDL conference. And there, Reinhard von Hangsladen, who's a professor at Kiel University in Germany, and his students were making a presentation. And Alexander Schulz-Rosengarten, who will be presenting today, gave a presentation that made us realize that there was a tremendous synergy between what he was doing and what we were doing. And so I introduced him to Marten, and within 2 days, they had actually put together a preliminary integration of our tools, and you'll see the effect of that today. So the project has grown quite a bit. There's quite a few people involved. Another key person is Soroush Bateni, who's from the University of Texas at Dallas. And he actually sent me out of the blue an email wanting to do an internship. And I get quite a few of these, but this one was particularly sharply targeted and fit our project. And so I jumped on it and started working with Soroush, and it really took off. And he has become also another powerful force behind this project. So that's just a little bit of the background. The project has been growing. We're welcoming other participants. It's very much an open source project, BSD style license. We encourage both commercialization efforts and research efforts, and it's a tremendous source of research ideas. It seems like every meeting we have another potential PhD research topic that comes out of this. So we hope it'll be as stimulating for you. So with that, I'd like to turn it over to Marten Lohstroh, who is going to give you some orientation on how to get started. So this is going to be starting out with just some logistics, and take it away, Marten. So just a little bit of background. Marten was a PhD student in my group, is now a postdoc in my group at Berkeley. And yes, so Marten.
Thank you, Edward. So is my screen visible? Okay. Yeah,
Yes.
I had some trouble getting the screen sharing started, but it seems to work now. Okay. So I will take you through some initial steps to get started. So let's see. So essentially, there are two options here. So we created something that is really robust and fail-safe, which is a virtual machine image that we already prepared for you. I will first show that. Also, we have a automated release system where our nightly build gets built, and this is downloadable from our GitHub site. And these pre-built packages are pretty easy to use as well on your native system, but should that fail, or do you prefer to use the VM, then the VM is a good backup option. So first of all, I sent out an email about this, but if you point to this webpage, you will find this Ubuntu for LF OVA image, and you can just download that. This is a pretty large file. It's like 5.8 gigs, I believe. Not too bad for a VM. But once you have that, you can start your favorite VM software. So I use VirtualBox. and you can boot that machine. Get rid of these. And it will be logged in automatically, as you can see here. And on the left-hand side, you will already see the icon of our integrated development environment, EPOC. So you can click on that, and that will bring up EPOC. So you can launch it. And that should get you going. That should get you started. Now, there is also a command line tool that is also pre-configured. So our command line compiler is called LFC, which should be on our path, which it is. And you can invoke it. There it is. And one issue that you might have is that, perhaps it doesn't come with the right resolution. You can change those things manually by either doing scaling or going into the settings, where you go to the screens. There are also some features in the virtualization that are enabled using what's called guest editions, and those are actually you can mount them using this option here, guest editions CD image. I already selected that, and when you click on that on the left hand side, you could install those. So let me turn off this VM and go to the other installation. So this is our releases page. And you can see here, we have one alpha release. We're on our way to a beta version. This is the nightly release that I triggered last night. And it comes with several assets. So it has here the source code, but it also has here LFC, and it has 3 different kinds of IDEs. So it has a Linux one, a Mac OS one, and a Windows one. So click on the one that is suitable for your platform, just save it, and then do the same with LFC. There's a zip version for Windows and a tarball for the others, and you can go ahead and download that. And then all you have to do is put those in a directory somewhere. I think I put them in a directory called ESWEEK. And I extract them. And then we have these, do that. Extract here. This one too. And then the last thing we need to do, so we can see in here, there is the application that we started earlier, EPOC, and also there's LFC, which here in this binary directory has a little script, and there's a jar that gets invoked in that script. The last thing that we need to do is add these to our path. So in most distributions, the directory local bin is on the path. You can also make sure by looking at a file like .profile in your home directory, and you will see probably something like this. If it's not on your path, so you can echo your path. If it's not on your path, then you have to add it either by putting it in your .profile or in your bash RC. I already have it on my path, so I don't have to do that. And what I then did was in this directory here, which is on my path, add a symlink. So you can see here, I did something like ln-s, and then the LFC that I just downloaded, and I call it LFC. And then as a result, you see here this symlink. And now if I do which LFC, it points to this symlink, and I can execute it. It's having a hard time finding the jar. So I'm not sure why the command line compiler is not correctly invoked right now. I have a lot of people watching over my shoulder, so if they have any suggestions, they're very welcome. We don't need them to continue right now because we will be using debug. So you first have to select a workspace. I call it ESWEEK workspace. And here we are back at the same place where we were in the VM. So I think now would be a good time for folks to ask questions, see if they're on the same page, report any problems.
Okay, so I'm going to pause the recording, and if anyone would like just to turn on their video, feel free.
Okay, so we've successfully started Epoch, and we've pre-configured Epoch so that a number of examples that we will walk through are very easily accessible from within. So we can go here and create a new Lingua Franca project. So in the package explorer, you see this. If you don't see this, you can go to File, New Lingua Franca project, and then we just have to give it a name. So let's call it example 1. Doesn't really matter. So here are a number of templates, which are a little bit more than templates at this point. Actually, these are essentially a number of examples that we'll go through during the tutorial. So let's start out with Hello World. So because Lingua Franca is a polyglot language, you can choose which version of the program you want. So we'll look at the C version right now. And it will create a project on your left-hand side. And then there's going to be a source directory that will have an LF file in it. So here you can see, put the diagram down here, I guess. Console as well. And if I save this file, a number of things happen. And you can see here that it's being compiled using CMake, actually. You can see that in the console. So what does this do? There's only one reaction in it, and it's triggered by startup. And this is the very first event that happens during an execution. And in the body, you see here what is actually plain C code.
Can I interrupt a second? Can you make your font a little bigger? This is graduate student size font, not
Okay,
professor size font.
Thanks for catching that. Sure. I don't know
Better.
why. Oh. I don't know what this was. That it just mirrored it.
That's an Eclipse feature that you can split the screen, but I don't know how you get rid of it.
I
There you
just
go.
fiddled with my keyboard and it went away. So in the reaction body here, this is just plain C code. So I think we've recently also added capability of showing a terminal, should you want access to one. So you can show other, where is it? How do I add the terminal?
It's under window show view, not
Show
perspective.
view. Ah, right. Terminal. And we can go to the directory where we were. So I think we were in ESWEEK workspace, and we can see our example there too. Now, if we go into the example directory, we'll see that there's now a bin directory and also an src gen directory. In the src gen directory, there is our generated code. So there's a bunch of files here that are essentially the supporting runtime. And there's also the hello world.c file, which is the generated code for this particular program. And you can see here what it actually looks like. And the C code is not necessarily super readable, but you can vaguely kind of relate it back to the code that we saw earlier. So there is here an info print statement. That's the one that we had over here. Here is some initialization of the reactor around it. Here's a routine for deleting it. And so there's a whole bunch of boilerplate that goes around this that you don't have to deal with. Yeah, this is what it looks like. Okay, so now let's embellish this example a little bit to get familiar with some some language features. So one thing that we can do is, instead of triggering this once, so let's first run it once. Obviously, so there it is. We executed and we showed hello world. So now let's assume that we want to do this not once, but we want to do this periodically. We can also create a timer and let's call it T. We'll have to give it a type as well. Timer T. So the first thing we have to do is give it an offset, and then we also have to give it a period. And then we can introduce this as a trigger. It doesn't actually matter because we specified 0 here. It will coincide with startup, so we can leave startup here or remove it. It doesn't matter. And we can now print it periodically, and it will go every second. Also notice here that I give integer values with a type. You're not allowed to do something like this. The compiler will complain and say, well, you're specifying units here, you're specifying a time here, but no units. And so you have to specify units. So currently we only have one main reactor, but we can also factor this out and make it a little bit more interesting and create some components. So instead of just printing it, let's create a printer component. So we create another reactor, which is we call printer. And of course, in order for the printer to do something, it'll have to have an input. So we create an input. The input has to have a type. Again, if you omit the type, the compiler will complain. And then we have to have a reaction that is triggered by that input. And we can just copy this guy in here. And so now we can get rid of this because we have factored it out into a separate component. We can instantiate it. So we can, in the main reactor, say P equals new printer. And now we have an instance of that printer reactor that we can refer to. So now let's create a reactor to put the periodic to produce the periodic inputs. So let's call it counter. But to build a counter, we have to, of course, have state as well. So let's create a counter. So we have to introduce a state variable. We call it count. Also, this is of type integer. And then we have to create our reaction. Notice the funny brackets here that I'm using because within funny brackets, what you have is straightforward target code. We have to also have a trigger, and we already created one here, which is this timer. So we just put it in there, and then we have to specify it as a trigger, and then the errors go away. And then, so what does it have to do? Well, it has to produce an output, right? We want to get the output to the printer. So let's add an output port as well. And then in the reaction, we're going to use a routine called set, which in the C runtime is just a macro. And we refer to out. And then we also need access to our state variable, which in the C runtime is accessible through the self struct. So you saw the boilerplate plate we discussed earlier. There will be a self struct in scope that we can refer to, and the same holds for this variable out. But this won't fly because out here has to be declared as an output. Otherwise, out will not be in scope. So we now set out to the current value of the state variable count. And then, of course, every time we invoke, every time we get triggered, we want to increment the counter. So self count. And I'm just going to add 1 here. Okay, so now we have a periodic counter, but we haven't instantiated it yet. So let's do that. So let's say C is new counter. And now we have 2 components, but we haven't connected them together yet. So how do we do that? Well, we have syntax for that too. This is in Lingua Franca. You can refer to an instance, C, and you can find its output port. You can see here that this is content assisted. And then we connect that to the input port of P. And I can also use F3 here. So if I click on in and hit F3, then I go there. So now these two guys are connected. Okay, so let's see what it does. It has already compiled in the meantime, so that would have been visible here in the console. In the terminal, we can now invoke this, and now we have a periodic hello world. Now we can also play around with this a little bit and augment it a little bit. So one of the things that we can do is parameterize reactors. So one of the things we can do is, for instance, add a stride parameter to the counter. So I have to provide a default value. So what comes after the colon is a type annotation, and then what's between the braces is the initial value, and we just initialize it to 1. But we can then go in here. So let's first of all let's use it in our assignment, right? So the parameters are also made available in the self struct, so we can refer to it now. And this won't make any difference, right? I mean, we haven't set the argument yet, but notice also that we're not printing it yet. So perhaps we want to print it here on the downstream side. So we can do that by referring to the incoming in that triggers it. And now we should be able to see that it's counting. Okay, yes, it is. But now what we can do is say, well, sure, I want my counter instance, but I also want to parameterize it differently. I want a different stride. So I'm going to say stride equals 10. And now when I rerun the program, it will count in chunks of 10 instead of 1. So we've covered timers. We've covered state variables and parameters and how these are brought into scope through the self struct. This is a target specific mechanism. Each target will have its own way of doing this. The syntax will look slightly different, but that's okay because it's not Lingua Franca syntax. It's within these funny brackets. And we have talked about triggers, and we have talked about effects. And let's see, is there anything missing here? I think that as far as this Hello World example, we've covered everything.
Great.
Yeah.
Thanks, Marten. So you might have noticed as Marten was going through this little diagram at the lower left that was automatically getting updated as he was typing, and that will be that diagramming capability was developed by Alexander Schulz-Rosengarten, who is a PhD student in the group of Reinhard van Hanksladen at Kiel University in the north of Germany. And so, Alex, I'd like to turn it over to you, and you can walk us through a little bit of the capabilities of that diagramming capability. Thank you.
Yeah. Thank you, Edward. Yeah, you probably already noticed the diagram. So in this setup, it's here on the right, and it's an interactive visualization of our Lingua Franca program. And the idea is that it's always automatically generated from the source code of Lingua Franca. And the key enabler to make this possible is automatic layout. So all these elements and edges are automatically routed and arranged, and no manual arrangement is necessary. And this differs a bit to other modeling languages where you don't have a textual definition and a graphical model. But here, this is kind of a scenario where the best of both worlds come together. And they are also tightly coupled together. So if I select here the counter, the corresponding reactor is actually highlighted in the text. And I can expand this one and look into its details and select the ones I'm interested in. Same for the printer. And if I quickly copy this counter here, you can see the diagrams automatically refresh. And now we can look into that counter and drill level by level, drill down into the details of a model. It's also possible to adjust these details that you can see. For example, here on the right, there is a sidebar which provides several options. I can activate the instance names here for the reactors, and I can also show the parameters that are available in each instance, and they're actually reflecting instance-based values. So in the general form, the reactor has a value of 1 for this stride, and this one has 10, and this one has 5. So the diagram always represents the actual values for these. These visualizations are not only helpful for understanding the program, but also detecting problems. So let me quickly hide the details and then introduce a problem. I will introduce a causality loop, which will be explained later, but I simply add an output and reroute a connection. And now you can see the diagram is indicating a problem, because we here have an immediate feedback that is a causality loop, and that's a problem. And now the diagram can be used to, for example, show all the problems. In this case, it's rather easy, but these problems can span the whole topology of the program. And this helps you to focus on the problem. So for example, you can also filter out all the elements that are not involved in this actual cycle, and you can focus on the problem in order to solve it. So let me quickly here solve it by rerouting the dependencies a bit. And now you can see the error is gone and the diagram is back to normal, and you can continue creating your program, and the visualization is aiding in this process of modeling Lingua Franca programs. Thank you.
Thanks, Alex. That was great. I want to emphasize that we're very lucky to be working with Alex and Reinhard van Hanksladen's group, because they are really, I consider them to be the world's top experts on interactive program visualization. So we're really benefiting from that. So I would like to emphasize that the little funny curly brackets that that you see here are a very important aspect of this language. Okay, and it's important to understand that Lingua Franca is not a programming language. It's really a coordination language. It's not meant to replace your programming language. So there's the notion of a target language, and the target language is a conventional language. So what you've seen so far is the use of C as a target language, where the code generator generates a standalone C program. We currently have 4 other targets, one of which is still very much in development, but C++, Python, TypeScript, and Rust. The Rust one is a little less complete at this point, but I'd like to introduce next Christian Menard, who is a PhD student working with Jerónimo Castrillón at the Technical University of Dresden. So Geronimo holds the chair for compiler construction in Dresden, and he has a really hotshot group of students working with him, and we've been very lucky to be working with several of them. Christian was the first to fully engage with this project and has been very instrumental in the development of the language. And he single-handedly built the C++ target, which has a number of features that he'd like to show you now. So Christian, take it away.
Hello, everyone. I want to show you a simple example of a C++ program in Lingua Franca. And I will quickly walk you through this. So the first difference is, of course, that we set a different target. So we say C++ here in order to generate C++ code out of the program. And then what we embed in all the directions is actually C++ code. But also the code that we generate from the Lingua Franca program is C++ code, and we can have a look at this in a bit. And of course, we also utilize the language features that C++ provides compared to C. So we have classes, we have templates, and actually vectors become translated to classes in C++. And we can also utilize templates. So I did a modification to this counter vector that we saw earlier in C, and I made it generic by adding this little t here. This is a feature of Lingua Franca, and this gets translated to a template in C++. And then we can count any value. We could make this an 8-bit integer. We could make this a long. We could also use some type that implements the increment operator. So this reactor actually does the very same as we've seen earlier for the C version. It's made it a little bit more complicated. So for instance, we can actually define methods. So since this becomes a class, we can extend it by arbitrary methods and then facilitate code reuse. And we can call this actually from a reaction. And also state variables, they become member variables of the class, so we can actually directly reference them, same as for parameters. So we can directly access count and stride and operate on those. Also ports become objects, so that we can set on them. It's not a macro like I can see. And then we can send this count out. And the same for input ports, as we will see in a second. But before we do this, I quickly want to show you the generated code. This is the header file that's generated for this reactor. And it's a class. It's templated because of the generic t parameter. And then it has a bunch of things in it, like the timer and other things, like defines reactions, it defines the ports here in the bottom, also constructor is created. And actually what I said earlier is it's not quite true. So it's not a single class that's generated, but actually two. There's an outer one and an inner one. And that inner one is actually the scope that you see as a programmer when you write reactions. So in here, reaction bodies get defined, also the parameters get defined, state variables. And basically this is everything that you see that you can reference from within the reactions. Also methods. So the leak method is defined here. All right, so I extended this count and print example that we've seen earlier by a reactor that I put in the middle here. It's the hello reactor. And what it does is it takes as an input a t, and it produces a hello message of type t, this is quantified by t. And this hello message is a type that we defined ourselves. For this, we can use a preamble. That's like a prefix that's inserted at the top of the program. And we define the struct here that is just a value of type t and a string that identifies some message. And in order, so this is basically to show that you can also send more complex types than just integers, right? And in order to highlight how this works a bit in C++, I made this a little bit more complicated here than necessary. So actually, all of the values that you send via ports in the C++ target are smart pointers, so reference counting pointers. And this allows you to ensure that there are not any data erases in the program. So in order to create such a smart pointer, very similar to what the standard library provides here, there's this make mutable value function, and it creates a pointer to a header message T. And then we can modify that. So we assign the message here, which is given by a parameter, by the way. And we also assign a value, which we got from our input. And we retrieve the value by calling get on the input. And this will also return a smart pointer. Hence, we have to also dereference that to actually obtain the actual value. And we copy that then to our new message. And when we completed operating on this data object, we can send it out. And actually, we have to use move semantics here. So we use the C++ move operator to move the ownership of this object, of this value, out to another actor and to actually send it to somewhere else. Afterwards, the reference we got will be invalid. And this really ensures that once some other actor operates on that, it's guaranteed that there are no other references, especially not mutable references to that value, so that there could be data erases or something. All of this usually you don't have to do by hand. So there's this most of the time works implicitly. It works implicitly in the case for where you just send a simple integer. And also for more context types, you can just create them directly and they will be automatically framed in these smart pointers. But sometimes it's quite useful to do it this way. And finally, we got the print reactor. This is very similar to the print reactor we had seen before in C. It only uses a slightly different method of printing the data. And also in this case, it's not just printing hello, it's printing the message that it receives from the hello reactor, which by default is also hello. All right, so let's run this quickly. Clear this first. And when we run this, it's doing precisely the same as the C example that we've seen before. It's saying hello every second, and it's showing the count that is incremented by 10 every time. Now, there's another interesting feature that I would like to show you, namely that C++ is a bit more flexible, more dynamic in its runtime, and it doesn't need to know so many static things when it's compiled. And this is also used to make the application configurable. So actually, I have defined several parameters on the main reactor here. And these translate to command line parameters that I can use to configure the program. And in this case, I can slightly modify the behavior of the program, but I can also do very complex things with that. So for instance, I have here a version where I set this twice to 2. I want to have a period of 100 milliseconds and the message to be foo. I can fire that up, and then it more rapidly produces data, and it fires always foo at the current count. And I can actually use this to also change the architecture of the whole program, as we will see later. That's it from me.
Great. Thanks, Christian. Again, that's Christian Menard working at the Technical University of Dresden. So one of the things that I particularly like about this is the generated C++ code here is really quite beautiful to read. It's really quite a notable contrast with the C code, which is rather hard to make beautiful. Okay, so next I would like to introduce Soroush Bateni, and Soroush is a PhD student at the University of Texas at Dallas, and he's working with Professor Kong Liu, and Kong and his group are top experts in real-time systems, and so He brings a different angle on the project, and he has contributed an enormous amount. One of the things he did was he single-handedly created the Python target, which has a huge advantage of being able to pull in the whole ecosystem of Python into your Lingua Franca applications. So if I could turn it over to Soroush, it's all yours.
Thank you, Edward, for the warm introduction. Okay, so I have opened before me the Python version of the Hello World example that you've been seeing. And that, of course, is designated using this target Python. And if you look inside these funny brackets, which are definitions of reactions, part of the definition of reactions, you will see Python code, which in this case, you can see the print, ubiquitous print function. Okay, so the first thing to note about the Python target is, you might have already noticed, but the parameters, state variables, and ports don't have types anymore. And that's because the Python target follows the Python philosophy of duck typing, which is if something walks like a duck and quacks like a duck, it's a duck. And in this case, both counter and printer expect integers. And so what happens here is, and you can see this in this body of the body of this reaction, that what is sent on the output port is a state variable count that is initialized to 0, which is just an integer, and the receiver will just print it without needing to explicitly mention types. The other thing that you might have noticed is that, similar to the C++ target, the output port is an object. So then here we're calling a set method on this object to set values on the port. So if I save this program, you might notice on the right, on the console, and if you're using LFC, you will see that this in the terminal. But once the code generator is finished with generating the Python code, it will give you instructions on how to run the program. And it's very simple. So there is a Python 3, which you need for executing any Python code, and this generated tutorial.py, which is generated code from this .lf program. So if I copy paste this, you will see that it will be execute it just like other targets. So just to look at for a second inside that tutorial.py, if you look at it, you will see that what has happened here is, for each reactor that was defined in the .lf file, you will end up with a Python class. And then if you have state variables and parameters, they will be members of this class. And your reaction functions will be methods of this class. The other thing about the Python target is that it's built based on the C runtime to enable maximum efficiency. And if I scroll down, after the reactor classes are instantiated, there is the main function, which calls this start, which is a magical function that will fire up the C runtime, and the C runtime will take it from there. So it will be in charge of handling events, executing reactions, and so on. Okay, so one of the major benefits of the Python target is that you have access to a vast library of Python modules. So to demonstrate that, I've created one example which actually uses a deep neural network, an object detector called YOLO. This is version 5 within Lingua Franca. So you can see the architecture of the program down here, which is very simple. So there is a webcam reactor, which is in charge of obtaining frames from my webcam here. There is a DNN module, which contains the DNN itself. And the results of that, so this DNN will take frames from the webcam reactor, and it will produce labels, object labels, based on that frame, and also coordinates for those object labels. And these two, together with the original frame, are fed to this plotter, which then will demonstrate the results. Okay, so let me run this for you. I need to disable my webcam so that this application can use it. Okay, so saving this and executing this. It will take a little bit, but then you might be able to see the results here. You can see I strategically put a chair behind me. And you might, on the right-hand side, see some output from this. You can see that it says received the DNN output late by about, this is about 1.5 seconds. But it is only for a few frames. So the reason for that, and Edward, I think will explain this later, is what I did was I put, get rid of this. Oops. So I put a deadline of 50 milliseconds on the outputs of the deep neural network. And what has happened here is that at least during the startup, that 50 millisecond has not been sufficient. If I make this deadline here, which is a parameter, if I change it to 10 milliseconds and run the application again, you will see that I will get a lot more deadline violations here. Generally, I think a conservative deadline for this DNN on my PC is 30 milliseconds. So 10 milliseconds is too small of a deadline. Another quick thing to note is that the way this program reads webcam frames is using a physical action. And again, Edward will extensively talk about this, but a physical action inherently is a tool for a Lingua Franca program to obtain physical events. And what will happen is when this physical action is scheduled, the timestamp is assigned to the event based on the underlying clock. What is triggering this physical action is a concurrent Python thread that is running in the background, and it's constantly calling this read from the camera. And as soon as it is able to obtain a frame, it will call this physical action, which will in turn start the whole pipeline. So this deadline will be relative to approximately when a frame was produced. However, you don't have to do that. You can actually drive the webcam reactor with a timer. So I have another example here. Here, instead of a physical action, the frames are actually obtained using a timer. So you can see that there is a timer with a period of 60 milliseconds. And every time that timer ticks, it will try to read a frame and then produce a frame. And you can see that there is this 3-second offset, or in real-time systems, what they call phase, because the warm-up time for this application is about 2-something seconds. And if I run this real quick, you will see that I will miss a lot more deadlines. It's just because this timer is blocking the program until it can read something. And the likelihood of missing deadlines is quite high now. So there is a trade-off here that you might consider. But with that, that concludes my demo. And so back to Edward.
Thank you, Soroush. That was excellent. So this ability to exploit the ecosystem of Python is a really very powerful thing. And so I'd like to introduce next a Berkeley student, a senior in our EECS department, Stephen Wong. So Stephen joined the project just, I think, 2 or 3 weeks ago. And so he, I think, is a kind of good existence proof of the ability to ramp up pretty quickly. And he's going to show us a couple of examples that he has built in the Python target. So Stephen?
Hi, let me share my screen first. Hopefully all can see my screen now. So as Edward mentioned, and Soroush also in the Python target, it has the power to import or utilize packages that are already existing in the Python ecosystem. And that's also one of the main strengths of using Python as a programming language. And here I've written a program in Lingua Franca, which utilizes the Pygame package to build a piano. So I'm currently in the directory of this Lingua Franca program, and I can use LFC, which is the Lingua Franca compiler, to compile my piano program. And also, because the piano program has sound, I might have to reshare, because just to double check, I enabled share sound. Yeah, I'm sharing sound now. So if I run this program, a Pygame interface would pop up, but it would take some time because of the library. And after I showed the a working piano, I can briefly describe how it's achieved in the Lingua Franca program. So, okay, here's the piano. Are you able to hear it? Nice. So the piano is rather simple. It looks simple. So whenever I press the characters that is labeled here on my keyboard, I can play sound, and I can also play black key as well, several keys at the same time, chords. Right. So here's the code for the piano program. I'll go over the diagram briefly. So at the beginning, I first initialized the audio system of the program. And after the audio system is initialized, it will send init signal to other components of the program, and it boots up other reactors, and then eventually starts the GUI, and then there's a loop of getting user inputs and then translating the keys of my keyboard, like the key presses, into musical notes, and then it'll send requests to update the graphic of the GUI. So everything done here is a blocking. So whenever I press a new button, the graphics update. If I don't do anything, it's blocking, so it won't take up much of my CPU. So that's the gist of my demo. Also, inside this Lingua Franca program, another thing I could do is I could also include Python files. So I'm currently including another Python file, right, that implements some part of the program. But then the main work of connecting all the components together is built in Lingua Franca. And that's my demo. Thank you.
Great. Thanks, Stephen. I'm really personally looking forward to playing with this and using the timing features of Lingua Franca to try to get creative with it. It looks like it'll be a lot of fun. So the next target language that I'd like us to cover is TypeScript, which is a dialect of JavaScript. And you may know that JavaScript is one of the top languages used worldwide, and there's a whole ecosystem around that as well. That's much more focused on web integrated computing. So I'd like to turn it over to Marten Lohstroh, who has been the person primarily in charge of this target. Marten, you're in charge now.
Cool, thank you, Edward. Yeah, so before I continue with the TypeScript target, I wanted to briefly mention something that I had overlooked in my C explanation. So the target properties that were featured in the code that we've seen so far. So you can actually add information to the target, and one of the commonly used target properties is the timeout. And so you can specify timeout to let the program terminate after a set time. I hadn't explained that. Another thing that I also wanted to point out is that we have some pretty neat error handling specifically for the C target, where we use line directives in the generated code to figure out where problems are. So as I said, I was very disciplined about saying, well, this reaction, it creates an output, so I have to declare that. But what if I'm forgetful and I don't? So let's remove that. And then we see that you actually get an error here, compilation error, because the out variable was not brought into scope. This is really critical to having accurate descriptions of what the components can do, and that's what our runtime uses in order to be able to safely exploit parallelism and so forth. Okay, so that was just an aside. So moving on, let's go and create another Lingua Franca project, which is, let's call it example 2. Let's create a web server. So this is an example written in TypeScript, and just as Python, opens up to a wealth of existing software and packages that you can use, so does Node.js, and that's what we're using. TypeScript can compile down to JavaScript, and that can be run using Node. So that makes it also very easy to build a little web server. So the idea is very simple. So we have, let me make this slightly smaller so that, oh, I'm getting that again. So we have one reactor. It has a state, which is just really a node module called HTTP that runs in the background. And then it has a physical action, which allows a reaction here to be triggered asynchronously. So whenever a request comes in from somebody that is trying to reach this website, a physical action gets triggered becomes active and then triggers this reaction, and that will formulate the response and pipes that back into this web server object that was created. So we can quickly have a look at what that looks like. So these TypeScript programs are actually created as if they were, let me, ESWEEK. Oh, I think. So if you look in the src gen folder, that's where the TypeScript code gets put. So let's look at this with code. If it's willing to do that. guess it's not. So the idea is that whatever you create with the Lingua Franca program is that you can publish it using npm. So you'll see here in srcgen that there is a package.json with some dependencies, and you can also edit those, and you can add modules that you want to use, and then our compiler will automatically pull in those dependencies and use them. So if we now want to run this, we can just invoke node. So in the srcgen directory, there is a dist directory, and that has a plain JavaScript code, plain JavaScript file that you can invoke using node. So let's do that. And that shows me that there's a web server running at port 8000. And so let's open a browser window. Let's see if that works. And it does. So now this is not a very fancy demo, but of course this, clearly shows, the extensibility, the advantage of being able to use all of these node modules. And it would be pretty straightforward to build some nice web applications out of this, and also to use it as a user interface component that could be a front end of perhaps a deeply embedded system or something like that. So I think that we're a little late, so let's not look at the generated code. I just wanted to mention two things. First of all, I've gotten help building this initially from Andres Groens. Later, Matt Weber contributed to the TypeScript runtime, and now also Hokeun Kim is actively involved in maintaining this. And the other thing is, I don't know, I forget. I think that was it. Back to you, Edward.
Okay, good. Thank you, Marten. Again, Marten is a postdoc at Berkeley. The languages that you've seen so far, C is, of course, the least safe of all. C++ allows you using, for example, these smart pointers to be a little bit safer. TypeScript, of course, has both the stronger type system of the TypeScript extension of JavaScript, which is an important thing, and also, this kind of web programming ecosystem and the ability to use kind of security features. The most interesting, from my perspective, recently developed language is one that kind of shares the efficiency of C, but with really very modern safety concepts in mind, which is Rust. So I'd like to introduce Clément Fournier, who is a student at the Technical University of Dresden. He's been working also with Jerónimo Castrillon's group in the compiler construction chair. And so take it away, Clément.
Thank you, Edward. I'm going to share my screen. All right. So so for those of you who are unfamiliar with the Rust programming language, it's basically a systems programming language. So it's low level enough to do some to program in embedded systems. It supports things like direct memory access, pointer arithmetic, and most importantly, it has no runtime GC. But it still provides strong guarantees about the memory safety of Rust programs. For instance, so it uses its type system, which uses an ownership system to track the lifetime of every value, and to guarantee, for instance, that all references actually point to valid data. So that prevents use after free bugs where you access garbage through a pointer, which is kind of a common bug in C and C++ programs. So this safety is a big, like a big advantage of Rust, also because it's asserted at compile time. Another attractive feature of Rust is that it has also a big ecosystem of libraries and also good support by different tools and IDEs. And with that in mind, well, that's why we want to support the Rust target. So the support for the Rust target is still very much experimental, but I'd like to show you a small example program, which is, well, it's a demo level program. So it's a snake game. So it's a terminal game where the rendering logic is just building a string that represents the board game and the snake, and just doing that at repeated intervals. So the interval at which this is done shrinks as when the game well becomes more difficult. So the more I eat food with the snake, the faster it gets. And this is all implemented using Lingua Franca's, well, by relying on Lingua Franca's semantics for timed events. So so this kind of rendering loop is actually implemented with Lingua Franca primitives. So we're going to look now at the implementation of this. So here I have the program opened in Epoch. So it fits into 3 source files. We have a main source file snake.lf, where the main logic of our application is in there. So it's pretty short. Each reaction is pretty, well, short and to the point. We have a keyboard events reactor, which is whose main purpose is just to handle asynchronous keyboard events, and a snakes.rs file, which is a pure Rust file, and which implements our model classes and basically the business logic of our application. So it's also pretty short, but yeah, the main point of showing you this is that part of the program can be written in pure Rust and be linked seamlessly within this LF program. Another thing that is interesting is that we can actually use the LF, well, the cargo tool, which is the build tool for Rust packages. It's also a package manager, and so we can add dependencies on crates, which are modules like in the Rust terminology. So we can add dependencies on external libraries, which in this particular example allow us to like handle keyboard events for our snake example. Yeah. So another interesting thing which we can see here is that the main reactor also can take parameters. So this is similar to C++, to the C++ feature. So you can also mention these parameters on the command line. We have automatic help generation. Like if I do that, we also have like these parameters here. So this is just a nice feature. So about the design maybe of this application, we have this diagram which helps us grasp how everything is relates to, I mean, is interconnected. So we have our main snake reactor, and within the keyboard events instance, yeah, to which, and every time a keyboard, an arrow, yeah, every time a key is pressed, then it emits an event here, which is handled by the snake reactor. Here we can see the actual loop, which I was referring to earlier. So this is the refresh loop, which executes, well, each iteration is spaced with a delay that shrinks as when the game speeds up. And every time the loop, I mean, on every iteration, this refresh screen reaction is called. So taking a look at this, so this is actually generated into a Rust function with parameters that correspond to the dependencies that are injected. So if you don't declare a dependency, you can't access it at all. You don't even have a reference to it. And the self here, so Rust is also kind of object-oriented. And so the self keyword actually means it's like the this pointer in C++. So we can access the state variables that are declared on our reactor like this. So here we have, yeah, we access the snake state variable and also the grid. And this is like the main function which implements like the stepping forward of the snake and computes the result. And then we can use pattern matching, which is also a kind of high level feature of Rust, which makes it very nice to program with. And we can execute a different action depending on the result of this function. So for instance, if the move that the snake took was illegal, like the snake bit its tail basically, then the function will return game over, and then we can request that the application be stopped. So this reads quite nicely, like context request stop ASAP. The context here is an object that is implicitly injected, like in addition to all the dependencies here. And it's basically the object with which every reaction interacts with the scheduler. And so here we ask that it request stopping the application. We could also tell it to stop the application after a short delay, like 2 seconds, just the time, for instance, to print a message or something. And for this, we can use this syntax, which is a call to a Rust macro. So this is Rust macro passes this string at compile time and expands it to to the Rust expression that would actually create a duration object, which represents a 2-second delay. So this is pretty nice, yeah, the Rust macro system. So yeah, diving maybe into this keyboard events reactor, we see here how we handle keyboard events. So on the startup event, we actually will spawn an asynchronous thread, which will block waiting for input events, but since it runs in the background, it doesn't interrupt the main thread and like the main event loop. And every time a key is pressed, then we're going to again use pattern matching to identify the arrow keys. And if the key was an arrow key, then we actually will, we'll send it back to our logical, to our logical synchronous event system, which will process it deterministically using the reactions we saw in the other reactor. And what's interesting here and what is that this is an example, I mean, we can use this as an example of the safety that the Rust type system buys us, since, this thread is actually has a type which isn't seen here because Rust has elaborate type inference, but the type of this thread actually forbids the thread from taking references to, for instance, the context, because the context object will actually be destroyed before the thread is actually destroyed itself. So if we take a reference to it like this, at some point the reference will become garbage, and this is disallowed by the compiler. So if I actually write this and try to compile it, I'll get a compiler of the Rust compiler. So this is also nice because capturing a reference to the context and putting it in a background thread and invoking methods on it asynchronously would basically completely break the semantics of our reactor program. So yeah, we can use the type system of Rust to actually guarantee that we don't do silly things like that. Yeah, I think my time is up, so I'm going to pass the mic back to Edward. Thanks.
Okay, Clément, thanks very much. So that was a sort of quick overview of the various target languages. It emphasizes that, that Lingua Franca is a polyglot programming framework and a coordination language rather than a programming language. It's not meant to replace your programming languages. Currently, you cannot mix the languages in the same application, but we have done some experimentation with multilingual programs, and we know it is possible in certain circumstances to combine these languages. So that's an ongoing effort to develop that capability. So let's take a 5-minute break now, and I guess we will be available for Q&A, but I'm going to pause the recording. Okay, so I'm back, and what I'd like to do next is to go through a small example in the C target in Lingua Franca that I think illustrates a number of the key points and in fact might help to address some of the questions that have come up. So let me share my screen, and here we go. Okay. So here we have epoch, a fairly blank epoch screen, and I'm going to create a new project. I just go File, New Lingua Franca project, and I'm going to call this project. I can give it any name I like, but let's just call it tutorial, since that's what we're doing here. And I will just leave the default location. It's worth noting where it's going to put this project, because that's where all the generated code is going to go. So it's worth paying some attention to that. And I'm going to pick one of the project templates, which is this reflex game template. Now, this reflex game is a simple example that comes from it actually is originally something created by Gerard Berry, who was at INRIA at the time and was the developer of the SRL language. And he used this reflex game example many times to illustrate the properties of SRL, which is an extremely interesting synchronous language. So this project got created, and I want to emphasize again that the sort of in EPOC, the project structure is fairly straightforward. You have a bin directory, which is where the generated binaries go. You have a source directory, which is where the lingua franca sources go and any other associated sources. And then you have the source gen directory, which is where the generated code goes. So you can go and peruse the reflex game C generated C code if you like. Okay, so let's have a look at the lingua franca code. So this is an example that you can find. It's actually in the repo in the examples directory. And it's a fairly straightforward application, but it illustrates quite a number of the features of the language. So let me first start by just running the program so that you can understand what it does. So using this terminal, I have to, let's see, I have to try to remember where the project was put. So I think runtime eclipse.x text tutorial, probably, right? That looks right. Let's just check. So the bin directory has an executable that was created at 7:35 a.m. That's 2 minutes ago. Okay, that's California time. Okay, so this is in fact what was just created when I created the project. So if I execute this binary, okay, what the reflex game does is it simply prints some instructions. So it says watch for a prompt, then hit return or enter, and type Control D to quit. So it said, it gave me a prompt, hit return or enter. So I'm supposed to, as quickly as I can, hit return. Now that wasn't very quick. That was 8 milliseconds reflex time. That's pretty bad. Let's see the next one. Okay, 1.3 milliseconds. I can do better than that. Come on, come on, come on. Give me a prompt. Give me a prompt. Half a second. Okay. I could try anticipating, but if I hit return when I haven't been prompted, it detects that and tells me that I've cheated, and it exits the program and reports my average response time, which was pretty pathetic. So, okay, so let's have a look at how this program works. So there's a number of features. One is that, first of all, it's responding asynchronously to external events, right? It's that's a key feature. And similar to that feature has been shown in several of the examples that you've seen so far. The snake game was responding to arrow presses on the keyboard. The web server was responding to incoming HTTP requests. These are all asynchronous events that get injected into the Lingua Franca program. And Lingua Franca then kind of takes over the processing of those events. And let me show you how that works. So let's actually, there's another thing, which is the generating of the prompts. So let me start actually with the generating of the prompts, because that shows a slightly simpler timing issue. So we have this random source reactor, and its documentation says it produces a counting sequence at random times with minimum and maximum time between outputs specified as parameters. Okay, so we have this reactor random source. It has two parameters, min time and max time. And these are set by default to 2 seconds and 8 seconds. So the time between prompts will be somewhere between 2 and 8 seconds. Now, here I show a feature of Lingua Franca, which is that you can include right directly into your source code a preamble, which is just arbitrary C code put into these brackets. And that can import other external C files, or it can define functions that you're going to use. So in this case, it defines a function that generates a random number and turns it into a time interval between the minimum and the maximum times. Okay, so it takes minimum and maximum times as arguments. So this is just an ordinary C function. So this random source has an input port, which is used to trigger a random wait. Okay, it's gonna, when it receives an input, it will then wait a random amount of time and then produce an output. Okay, it also has a state variable that it uses to count, and it has a reaction. Let's look at the details here. This symbol right here, it represents the startup event, and this chevron is the reaction to startup, and it declares that one of its effects is this so-called logical action. Okay, so the logical action is the way under program control that you request for something to happen in the future. Okay, this logical action has a minimum delay given by this parameter, which is set for this instance to 2 seconds. So this logical action will, when scheduled, so here in reaction to startup, I call schedule. So this is a built-in lingua franca function. This is the way that you request for things to happen on the logical timeline in lingua franca. So this says schedule the logical action named prompt for this amount of time in the future. Okay, what does this amount of time in the future mean? Every reaction, the body of the reaction executes logically instantaneously. It's invoked at a logical time. This particular reaction will be invoked at the startup time. Okay, and time does not elapse during the execution. So the additional time that is specified here is over and above that logical time point, the startup time. Okay, so that's very precise, and any two requests for a timed action in the future that happen to result in the same logical time will be logically simultaneous. There's no non-determinism in the ordering of those events. Okay, the logical time at which they occur determines their logical simultaneity. It's an extremely important feature of lingua franca, and it's a big part of what gives it its deterministic concurrency. So I've got this logical action named prompt. Now, I've scheduled it to occur sometime in the future. This second reaction is triggered by prompt and will produce an output out. So this reaction will be invoked at a logical time in the future, and it simply prints out the prompt, okay, giving me an index. You notice on the terminal, it was counting 1, 2, 3, 4, the number of times that this has occurred. Okay. And then finally, there's a reaction to another. When it receives another input, it simply calls schedule again with a new random time. Okay, so this is program control over timing. What about external events? Well, we can look at this get user input reactor. And again, it has a reaction to startup. Okay, here's the reaction to startup. But now the effect of this reaction to startup is a physical action rather than a logical action. Okay. Now what this declares is that a physical action is something that will be caused by some external event. Okay. And when that external event occurs, a call to schedule will be made. And at that point, the logical time will be assigned to that event based on the local real-time clock. Okay, so let's look at how that works. So in particular, in the preamble here, there is a function defined that at the time of startup, I create a thread that simply executes that function and passes to it this physical action. Okay, so let's look at what that thread does. What that thread does is just go into an infinite loop and use this built-in C function getChar to read from the keyboard, checks to see if I've hit a Control D, okay? And if so, it simply exits the thread. But if I've hit anything but a Control D, then it simply passes that character to this user response, And what's going to happen now is that a logical time will be assigned to this based on the physical time at which that occurs. Reaction 3 then will react to that physical event now at the logical time that was assigned when that external event occurred. And the first thing it does is check to see if I cheated. Okay, has the program actually issued a prompt or not? And if it hasn't issued a prompt, then it declares that that you cheated and it requests a stop. Otherwise, it simply calculates the elapsed time. And this is a time between the logical time at which the prompt was issued and the logical time assigned to this physical action. So it calculates the response time, increments the count, and then requests another prompt by producing an output, another. Okay. And then there's this reaction to the prompt, which simply records the prompt time. So that's how it's going to measure the elapsed reaction time, is it simply records the prompt time. And then finally, this symbol is a shutdown event. And so there's a reaction to program shutdown that reports the average response time. Okay. So that's all there is to this program. And I'd like to show you a couple of other features. Notice that there's a cycle in this program. Okay. Cycles are generally not a problem in Lingua Franca, but there's a little bit of a subtlety, right? If I go to the random source, and let me make a change in this program, a very seemingly innocuous change. I'm going to take this reaction and simply put it in a different order. This creates a causality loop. Okay, what's the reason for that? Well, every reaction of a reactor, this random source reactor has 3 reactions. Okay, these are mutually atomic. They share state. And so if one is executing, the other cannot execute until the one completes. Each execution occurs logically instantaneously at a logical time. It's possible for 2 reactions to be invoked at the same logical time. They have to have a well-defined order in order to have a deterministic behavior. So the order in which reactions are invoked at the same logical time is simply determined by the order in which they're specified. So if these 2 reactions are both enabled at the same logical time, 2 and 3, okay, then reaction 2 must be invoked before reaction 3. Similarly, in get user input, if reaction 2 and reaction 3 are invoked at the same logical time, then 2 must be invoked before 3. So that means that if 2 is enabled here, you must have a prompt at the logical time, which must have been produced by this at that logical time. And if another is going to produce an output at that logical time, it has to do so before this reaction can be triggered. And consequently, we have a causality loop, and there's no way to satisfy those ordering constraints. Okay, so the Lingua Franca code generator rejects this program and says, I cannot give you the Lingua Franca semantics with this program as specified. Simply changing the order of these reactions corrects that causality loop. So we discovered by experience that having this visualization of the causality loops is extremely helpful, because it's often quite difficult to actually be able to tell which of the what the source of the causality loop is. Okay, so this illustrates the difference between physical and logical time. Let me stop sharing. And the next thing that I would like to do is reintroduce Stephen Wong, who is an undergraduate at Berkeley. And again, he joined our group 2 or 3 weeks ago and started working on this, and quickly picked up on this reflex game and created a version in Python with a much nicer user interface. So Stephen, you want to show us that version?
Sure. I'm gonna share my screen. So as I mentioned, reflex game really demonstrates some of the key strengths of or the functionalities of Lingua Franca. And the reflex game demo that I built in terms of logic is very similar to the one that Edward showed you. But instead, I used the Pygame library in Python to incorporate a much nicer user interface. So similarly, on my terminal, I'm in the reflex game directory, and I can use LFC to build the reflex game. And as it's building, I can explain how the reflex game demo works. So when I run the code, it first starts at the GUI. Once the GUI started up, it would notify other components to listen for user input as well as update the graphics. And whenever there's a new event generated by random source, it'll tell the update graphics reactor to update the GUI, and then so on and so forth. So let me try to run that. It takes a while. So here's the reflex game. When we run the reflex game, it first shows the introductory prompt. It tells you how to stop the program, how to begin the program. And it says press any key to begin. So if I press, let's say, a key on my keyboard, it'll tell me to wait for the prompt. And then once the prompt is ready, it'll ask me to press any key, change the color. When I press the key again, it records my response time, which is really slow. And then a second prompt will come out. And then if I press a key before the prompt, it'll show the same error message as in Edward's demo, which is you should, and then it'll also show you my average response time. So the purpose of this demo is to show that with the Python target, you can easily integrate, sorry about that, you can integrate other existing libraries into your Lingua Franca program quite easily. In fact, this demo only took me about perhaps 3 or within the day to write. And I just joined the project for 2 weeks, as I mentioned. So Lingua Franca is really easy to use. All right, that's all my demo. Thank you.
Thanks, Stephen. Next, I would like to reintroduce Soroush Bateni, who is also the author of the Python target. But he's going to show you, so he's from UT Dallas again, working with Kong Liu. And Soroush is going to show you an application in Lingua Franca that really depends quite heavily on being able to do things in real time. Soroush, take it away.
So it seems like I don't have screen sharing access.
Let me fix that up. Sorry. All right, because you're on in 2 roles. Okay, you should have access now.
Okay, thank you so much. Okay, so I'm going to talk about another fun demo that I would encourage you to try if you're using a Linux machine or a Mac OS machine. The Windows version of this demo is in the works. So please come back in a few weeks and we'll have that. But in the meantime, if you have a Linux or Mac OS machine, you can get the tarball for this rhythm example from this link, which is rhythm.lf-lang.org. We also have this example on our repo if you want to try that later. So I'm gonna go through steps. So I'm just going to download this here to my machine. So it was downloaded here. Whoops, I need to. Okay, so in my downloads folder, here is the rhythm example. Let's put it in a nice place. Let's just put it on the desktop. And so I'm just gonna untar this. And here is the rhythm example and the supporting files. So the way that I will use this example is in the epoch IDE that I've downloaded from our nightly build. I will just create file, new project. Just a simple project is fine. And I'll just call it rhythm. And instead of using default location, I will click browse and go to my downloads folder, desktop folder. That's where I put it, and just click on this rhythm and open it up. So now I have my rhythm example. Here is the .lf file. Okay, it just asked me if I wanted to convert this to an xtext project. Just if you see that, click yes. And here it is. I have the rhythm, and I can see that the epoch ID has automatically built binaries for the examples in this tarball already for me. But I think all we need to do now is just to run the example. So here's a terminal that I've opened, and I put the example in our desktop rhythm. Okay. And if LSA is easier on the eyes. Okay, so here's the bin directory that contains the executables for all my examples. So all I need to do is do bin rhythm. So I'm going to share my computer sound so that you can hear this example. So let's just try it. And when you run it, you immediately see that on the right, you're getting these dots and some exclamation points. And each one of these dots is representing time passing. So as the name might give it away, this is a rhythm-based example which produces sounds with rhythms. And the default rhythm is downbeat. So you see this exclamation point, that's when the downbeat is played. And the downbeat is a 16th note, which is a musical term for a very short sound or a note that you can play. So what I can do is I can choose one of the instruments here. For example, I can choose clave. And you should be able to hear the clave sound on the downbeat. I can use a different rhythms. For example, I can use a merengue rhythm. Or a samba rhythm. Notice that I changed the rhythm to samba, but it wasn't changed until the next downbeat. And that's a feature that I will demonstrate. The other thing that I can do is, I just muted the sound. So I can actually control the tempo of the rhythm by plus and minus. So I'm gonna turn back on the sound, and then I'm just gonna increase the tempo and watch here. So that's one of the other features of this example. So going back to the code to just talk about it a little bit. So this example was written by Edward, and it's pretty cool. So it really has two reactors. One of them, which is relatively simple, is a display waveform, which is defined in display waveform.lf file. And this is a simple reactor which has a list of audio samples. And what you can do is you can pass an index to this waveform port. And if you pass it index 0, it will, the next time you will give it a note, it will play a bass drum, and so on. And the brain of the operation is this rhythm source. And the interesting thing about this rhythm source is it uses both a physical action and a logical action. So let me make this graph bigger. So it uses physical action to process the keyboard inputs. And for that, we have actually a library called Sensor Simulator, which ships with our jar file and with our IDE. And you can just use it in your application by using this path, which is the library path. And what you can do is you can register a physical action with this sensor simulator. And then every time a keyboard is pressed, this library will automatically trigger that physical action. And the reaction to that physical action is responsible for taking the value, which is what key was pressed, and then do whatever it wants. For example, here, change rhythm and so on. And it also uses a logical action to control the tempo. The reason that it's not using a timer and it's using a logical action, similar to previous examples like the snake example, is because you can make the tempo faster. So by default, this logical action will be regularly scheduled every 200 milliseconds. That is the default size, the default length of a 16th note, which is a parameter of this rhythm source. But if you increase the tempo, then this time will get shorter. Yeah, so one last thing that I wanted to do was I wanted to demonstrate a very cool feature of Lingua Franca, which is, again, a deadline. So what I can do is I can create a reaction to tick, and I can put a deadline on it. And I can put a deadline of 250 milliseconds, which is a little bit larger than a 16th note. And what happens is I can print here that a deadline has been missed. And you can see the graph is updated with my deadline. And if I run the example again, so I will not turn on the sound, but you can see that now occasionally I'll get this. So not every time, but occasionally the deadline has been missed. And a deadline being missed means that the system is behind real time by one note at least. And you can react to this. For example, you can skip a little bit and so on. So this example succinctly demonstrates the tools that Lingua Franca provides for writing real-time applications and how you can detect any fault that can occur. For example, in this very time-sensitive rhythm application, if you're late, you can detect that very easily by just adding a deadline handler. And feel free to try this. If you're running a Linux machine, Zoom interferes with this a little bit because it uses a lot of CPU. But feel free to try this after the demo. And with that, back to Edward. Thank you.
Thank you, Soroush. So the program shows a 5-minute Q&A now. And we're running a little behind schedule. So I'm wondering if we should stick to that plan or any votes? Anyone would like to raise a question? Shall I pause the recording? Okay, for the next segment, we're going to talk about concurrency and performance. So I mentioned that in Lingua Franca that the reactions of a given reactor are mutually exclusive, you can't have two reactions within the same reactor executing at the same time. But if you have multiple reactors, the reactions within distinct reactors can certainly execute at the same time, and that's often very desirable, in fact. So we're going to start by reintroducing Christian Menard, who's again working with Professor Jerónimo Castrillón at the Technical University of Dresden. And Christian invented for Lingua Franca a very clever syntax for expressing very compactly fairly large programs with a lot of concurrency in them. And so, Christian, I'd like to turn it over to you to show that off.
Yeah, hello again. So I will start again with a simple example, and it looks again similar to what I've shown earlier. So it's three reactors. We have our counter, we have a printer, and an adder this time in the middle. So we want to perform some computation. Very simple in this case. We just receive a value from the counter, and if we increment it, by default, it's incrementing by 1. And I can just quickly run this to show you what it does. Single adder, and it's basically showing the same output as we've seen earlier for the pure counter. It just increments everything by 1. Now, let's imagine we want to solve a slightly more complex problem that has some concurrency in it. So let's say we want to add 2 values, and the addition should happen concurrently. The very simple thing I can do is just instantiate second adder. Let's name it A1 and A2, and let's maybe say this one it's to the input. Now the diagram updated, and I have 2 reactor instances. I need to fix my connections now. This is also shown by these error markers here. So I renamed or added new instances. So I have to adjust those here, and I actually also need to duplicate this connection in order to connect both of my instances. Right, and now the output of the counter, it's sent to both adders, and I add a different value. And since this is in different reactors and they're independent on each other, this can actually is concurrent, and it can actually be executed in parallel to each other. And finally, I also need to fix this connection to the printer. And in a naive thing I could try is actually to connect both outputs of the 2 adders to the same input port of the printer. However, Lingua Franca doesn't allow us to do that. If it would be allowed, this would be a potential source of non-determinism, because it isn't always clear in which order these messages should be processed, and merging is quite hard. So this is forbidden in Lingua Franca, and in order to resolve that, what we need to do is actually also introduce more ports on the printer. So we can just duplicate that port, have a reaction to both of the ports, and then I can also duplicate this so that both values are printed. And now I can fix my connections here. So if I were to run this, I would get the output from both adders, and both lines would be printed with slightly different values. Now, I guess you can imagine that this is quite tedious to do by hand for very large programs where you maybe want to have 10 adders or 100, or maybe have a very complex structure. So there's a neat shortcut for this. So instead of just creating multiple instances by hand, what you can do is create what we call a bank of reactors. So it's multiple instances which show up stacked in the diagram view. So it behaves like an array of reactors. And actually, let me make it slightly more complicated. So I'm going to introduce a parameter here, and I can parameterize the width or the size of this bank. And now we need to fix connections again, so let's reverse that change to connect the header back. The IDE actually at this point shows a warning. So it tells me the left width is 1, but the right width is 4, and it doesn't work. So what it tries to do is just, we have a single output port here, and it connects them to the first output port. It connects it to the first output port on the right side. And so it creates a single connection. In order to actually create 4 connections and to broadcast the value, what I can do is add this little plus here, which means broadcast, and then the output is replicated and forwarded to all the different instances of the header. And for the printer, I can do something very similar. So again, I'm just going to copy this. Let's introduce this parameter and also forward that to the printer. And now I can create a multiport. That's how we call it, basically an array of ports. And we have n ports here. I need to fix up this direction a little bit. So it directs to in. And now since we have an array or a vector in a C++ target of ports, what we can do is we can iterate over it. So let's create a for loop. This, and we can remove that, and we can adjust the output maybe a little bit. So this can print from which indexes it comes, and then it prints the value from the specific port. And so we iterate over the indices, and then we can access these individual ports. And then the last thing I need to do is fix the connection down here. So this creates a multi-port connection where the 4 instances of the header port, their outputs, are connected to this multi-port input, which is actually shown by this little changed triangle here that it's multi-port. I think I can also add the width here. And one final thing, change I want to make. So in order for all these headers to receive a different value, what I can do is just rename that to bank index, and that will be automatically assigned on instantiation, and each of the headers will get a different index. I can use it here. Now, if I run this, I will get output, of course, from the 4 different headers. Yeah, so it's printing this, and of course the first one, the index 0 adds 0, and so on. So the last one adds 3. And what I now can also do is I can play around with this parameter that we gave this n. So I can say, let's do this for 10 headers, or let's do this for 1,000 headers, and this automatically adjusts the structure of the program and instantiates vectors accordingly. And with this quite simple syntax, it actually allows you to build quite complex patterns and solve various kinds of problems in a neat way. And that's it from my side.
Okay. Thank you, Christian. So next, I would like to reintroduce Marten Lohstroh, postdoc at Berkeley, who's going to show us how these kinds of programs execute in parallel on a multi-core machine. Marten, take it away.
Thank you, Edward. Let me share my screen. Okay, so this is also something that you can follow along with. This is the same mechanism that we used before. You start a new Lingua Franca project. Let us call it parallel, and then select the parallel project template. So this example is in the same vein as the example that Christian just discussed, and the key here is to show that we get speed up from using multiple threads or workers. So the runtime is constructed such that the lack of data dependencies between reactions. So first of all, they have to be in separate reactors, and second, there has to be no data dependency between them. They are executed concurrently, and if the runtime allocates more than one worker, which it is capable of doing, if you use the threaded runtime in C, for instance, C++ uses a very similar mechanism, and that will allow reactions that are triggered at the same logical time instant to execute in parallel. And that, of course, yields a speed up. So this simple program here, the work is symbolized by this take time reactor, which really just sleeps for an amount of time. And it has a source that produces inputs that are taken by the take time reactor. As Christian explained, these are allocated in a bank, so there's 4 of them. And this gets plugged into the destination. So when we run this, I think it has already compiled. So let's cd into parallel. We get what we would expect. So the source produces events with a spacing of 200 milliseconds between them. And also there's a timeout of 2 seconds. So the program stops executing. Currently, this parameter here, this target property, denotes that it uses only 1 thread. So even though the dependency graph here clearly indicates that these take time reactors are in parallel, they have no dependencies between them, they don't share any state, they can be executed in parallel. There are no resources to do so. But if we provide those resources by saying, well, now take 4 threads instead of just 1, the program in the meantime recompiles. So you can look here at the elapsed physical time. So the logical time that elapsed is only 2 seconds, as we specified here in the target property. But the physical time that elapsed is significantly longer, and that is because there is not enough capacity of doing things in parallel. But if we add capacity, then we can get a lot closer to that goal of our 2 seconds. And you see, we're still a little bit late, but only by 200 milliseconds versus, a factor. So this is a very simple demonstration of exploiting parallelism. There are also other ways of doing that. Let me show another example. So let's open another project. I call this pipeline. There's a pipeline template here, and this demonstrates pipeline parallelism that is using the exact same mechanism that we discussed so far, exploits parallelism automatically. However, there are some caveats. So let's go into that. So here we have a pipeline Again, this is not about the functionality of the program. These are actually adapted examples from regression tests that we run automatically when changes are pushed to our repository. So these are kind of constructed simple examples that test particular things. But it's a good illustration of how we exploit parallelism. So here's a pipeline, and using the syntax from Christian, we have here this this pipeline construction where we have one reactor that feeds into a bank that is daisy chained. So you could essentially unfold this first time reactor, plug it after another, and then plug it after another, and then plug it after another. This is just a really compact, nice notation that signifies the same thing. Now, we allocated 4 threads like we did with the previous example, and let's run it. So let's go back up into here. So let's run this example. And the issue here is very similar. We're lagging behind logical time. So we specify it to send messages with a period of 100 milliseconds, but we're unable to keep up because we don't exploit any parallelism. But why is that? Because we allocated 4 threads. Well, it is a pipeline, and you have to, so at the first logical time in a pipeline, the first functional unit, which is our first time, take time reactor, has some work to do. And then if you construct the pipeline properly, then at the second tick, the first one and the second one have something to do, and so forth. But then that only works if if it's clocked. And so the problem here is that the functional units have no delay between them, and the delay has to match the period of the send count reactor. So here it matches. We're using 100 milliseconds. And when we fix that, and you can see here along all the edges, we introduce a delay, we immediately see a speed up. So this kind of really concisely shows how we make use of multi-core. Yeah, that was it. Back to Edward.
Thank you, Martin. So one of the things that we have been doing is assessing performance of Lingua Franca, and sometimes, as anyone who has experience debugging parallel code, it can be quite difficult. And so we've put some effort into building some tracing mechanisms that are by design designed to be very low overhead. So I would like to introduce another recent addition to the project. This is Professor Hokeun Kim, who is an assistant professor at Hanyang University in Seoul. Hokeun was previously at Google just until August. And before that was a PhD student in my group. And so we know Hokeun very well and have worked with him in the past. And Hokeun will show us around the tracing mechanisms that currently exist in Lingua Franca. Take it away, Hokeun.
Thank you, Edward, for the kind introduction. So I'll be presenting tracing mechanisms in Lingua Franca. In general, tracing is useful for recording and analyzing information gathered during the program execution, for example, for performance analysis, as Edward just mentioned. LF supports tracing tailored to reactor models. More importantly, LF minimizes tracing overhead by recording the information in a compact binary format. The events recorded in traces include calls to schedule events, beginning and end of reactions, worker thread related events, and user defined events. The timing of each event is also recorded, including physical and logical time, microsteps, and delays. If there are triggers for these events, those triggers will be recorded as well. And the full list of trace events can be found in trace.h file. Currently, tracing is supported in C, Python, and C++ targets. The C++ target requires Linux and third-party libraries, while C and Python do not require any third-party libraries. And you can find more information on the wiki. Okay, now let me begin the tracing demo. To enable tracing in a Lingua Franca program, you can simply add a target parameter called tracing and set it true. This tracing.lf program consists of source reactor, destination reactor, and 4 reactors running concurrently using banks and multiports that Christian showed earlier. And if you run this tracing enabled LF program like this, tracing.lft file will be created. This .lft file is a binary file, so we can convert it to human readable formats using utilities provided by LF. One utility is trace to CSV. When we run this, it converts .lft file into 2 CSV files, one for the row trace events and the other for a summary of events. Another utility is trace to Chrome. And if you run this, it converts .lft file into .json file that can be loaded into a visualization tool called Google Trace Viewer. And if you have a Chrome browser, you can run the Trace Viewer by simply typing Chrome://tracing in the address bar. And then you can load .json file that we just created and see the concurrent events in different colors. For example, you can see the tasks, the concurrent tasks, and worker wait events as shown here. In addition to these events, you can also view the user-defined events, this number of destination invocations, which are registered and recorded in the LF program. And if you open CSV files like this, you can see the row events as shown here, or also the summary as shown here. And you can enable tracing in Python as well. Yeah, let me just show you how so that this works. Example. As you can see, the .lft file is generated. Okay, that was about it for tracing in Lingua Franca. And thank you, and back to Edward.
Thank you, Hokeun. I would like to next reintroduce Christian Menard from TU Dresden. So Christian has been leading an effort that has actually involved several people to do some serious performance benchmarking in Lingua Franca to learn about the consequences of our choices in language design. And so Christian, if you can tell us where we're at currently with this these performance measurements, that I would be grateful. Thank you. Take it away.
Of course. So yes, as Edward said, we of course are also interested in understanding how well Lingua Franca performs compared to other solutions that are out there and that are used in various projects. And of course, then the first question is what to compare to. And we decided to compare against some of the actor frameworks that are out there, because actors are quite related to reactors. In a way, reactors can be seen as an extension of the actor model. And we also found a benchmark suite that covers various problems and implements them in various actor frameworks in order to provide a way to compare them. Particularly interesting for us was Akka, which is Scala-based and very popular in the JVM world, and the C++ active framework, which is very popular in the C++ world, and also quite competitive in performance. And so, as I said, we found this Serena benchmark suite, and we tried to port this to Lingua Franca. I said we tried because porting these actor benchmarks or actor programs isn't always straightforward, because the semantics of Lingua Franca and reactors are very, very different from the ones of actors. In actors, everything is asynchronous. In Lingua Franca, everything is synchronous by default. But we tried our best to capture the structure and of the programs and their behavior in order to allow a fair comparison. And what is seen here in this, what you see here in this plot is the results of a recent measurements I made. That's run on a 20-thread machine, and comparing the performance of Lingua Franca, the C++ runtime, the C++ active framework in green, and Akka in red. And actually, this graph is normalized to Akka, so Akka always has performance 1, and then if it goes up, it's worse, and if it goes down, it's faster. And what we can see is that I would say we are at par with both CAF and Akka. And some of the benchmarks, we are somewhat slower, quite a bit even here for those big ones, that goes way up. But for others, we are also really, really fast, like the cigarette smokers here. It's more than factor 10 faster than the Akka version. We are currently still investigating as to what the reasons are, and we believe we can actually pull down a few of these bars quite a bit. But for some benchmarks, the reason is also this mentioned difference between the semantics of reactors and actors. For instance, I believe this bank transaction here is lower because things are not handled asynchronously, and we probably can't do much about it. But on the other hand, there are some problems like the cigarette smoker problem here, which is a concurrency problem that can be solved much more elegantly and more performant in Lingua Franca. I would also like you to show 2 different plots just to give you an idea of how Lingua Franca programs can scale. So this is kind of zoomed in on 2 of the benchmarks. This is the ping pong benchmark, really simple benchmark, just 2 reactors, one says ping, the other says pong back, and then they go back and forth. And as you can see, the performance is quite stable if you add more threads. It drops down a little bit, but not too bad. Same for the C++ actor framework, although it's like factor 2 slower. And actually in Akka, if you add more threads, then you add more overhead and you lose performance actually. Reason being, of course, that there is no concurrency and no exploitable parallelism in the program. Another benchmark that has concurrency and exploitable parallelism is the all-pairs path benchmark. And here you can actually also see that Lingua Franca scales really well. So you add more threads, you gain performance. Same actually also for Akka, but it kind of stops at 4 threads and then stabilizing. And for the C++ active framework, it's also scaling, but then at some point it's going back up again. So it's kind of doing a weird curve. And interestingly, actually, Lingua Franca single-threaded performs worse in this benchmark than Akka, but if you scale it up, then it's better. So yeah, that's just to give you a brief overview of what's happening in this regard and where we're standing, but this is still a work in progress.
Great, thank you, Christian. So the last topic in the concurrency and performance section is a very exciting one to me, which is federated execution. So what you've seen so far is mostly Lingua Franca programs running on multi-core machines. But largely due to a tremendous amount of work by Soroush Bateni of UT Dallas, we can map lingua franca programs to multiple hosts and synthesize the communication between them across the network automatically. So I think mostly it's been Soroush. I've had some hand in developing this, and Marten Lohstroh also has had a significant hand in developing this, but Soroush is going to give us a brief introduction to this, what we call federated execution of lingua franca programs. So take it away, Soroush.
Thank you, Edward, for the kind introduction. So just to give an overview of what we're going to show here is first, I'm going to show you how we can create a distributed LF program. Then I'll show you how to execute each distributed node and how to deploy. And then I'll briefly talk about how distributed LF programs are coordinated. I'll talk about two coordination strategies, one conservative and one decentralized, which is much less conservative. For this demo, for the purposes of this demo, I will use a hello world, which is slightly modified. You can find this hello world example on our repo under the distributed hello world example in the examples directory. So feel free to try these. Our federated infrastructure is only supported on Linux and Mac OS. We have plans to support Windows in the future. Okay, so with that, I am just going to jump right into it. Okay, so just to briefly explain how this hello world example is modified. So we're still using two reactors, just like the other hello worlds that you saw in Python, C++, and so on. However, because we want to demonstrate that we have message passing infrastructure implemented in lingua franca, what happens in this example is actually that the message generator, the source, will produce a string which is consisted of a prefix and a number, and it will send that message to this print message reactor, which will in turn print that message. The other thing that we augmented this example with is we also utilize this lingua franca API, which is getCurrentTag, which returns the current logical tag or logical time of the application. And the idea is that we want to check that indeed the semantics of lingua franca are honored even in a distributed setting. Okay, so I have here an unfederated program. So it's just a simple hello world with a main reactor. And so I would need to get rid of the bin directory and the source directory. Apologies for that. Okay, so now I'm gonna, as always, save this program, this hello world program. And what I'm gonna do is now look in the bin directory. Whoops. I am in the wrong directory. Examples. Okay. So now I'm in the examples directory. Okay, so if I look, I would need to remove the folder again. Okay, so I'm going to recompile the program again. And if I look in the bin directory, what I will see is when I save this program, the lingua franca infrastructure compiled it and produced a binary for me, a hello world. So this binary contains both of these reactors. And the way that they communicate is quite easy. They actually just pass a pointer. So this message being sent from the message generator to this print message is just as simple as passing a pointer. So let me now execute this single application to see what it does. So the other thing this program is doing, as I said earlier, is also printing the logical tag at which things are happening. So if you look at these first two lines, you can see the message generator is producing a message at 1 second, and that is because it is driven by a timer with an offset of 1 second. And you can see that the receiver receives that message also at 1 second. Okay, and that is inherently the semantics of lingua franca, right? Which is that this execution of reactions is synchronous. Okay, so now the way I can make this program into a distributed version is very simple. So let me clear this. All I need to do is I change this main reactor to federated. And now if I look at the bin directory, now I can see here, you can see in this terminal that we no longer just have one hello world. Now we have 3. And we still have this hello world here, and I'll talk about that in a second. However, you can see that 2 new things appeared. So one of them is called hello world underscore print, and the other one is called hello world underscore source. And these names come from the instantiations of these reactors in the federated reactor. So you can see here that I have a source reactor, and you can see here that I have a print reactor. And the lingua franca generator automatically has created 2 separate processes for each of these reactors. Okay, so now you can take these processes and put them on different machines and execute them. However, to facilitate that kind of a workflow, we also produce a bash script. So if I look inside this hello world, you will see a rather sophisticated bash script, but really what it does is it will launch these 2 federates. And I can execute this by just running that bash script. Okay, and now you can see that you can see that essentially the way the program behaves is exactly the same as before. So you see that the source reactor is producing a message at 1 second, and the receiver will receive it also at 1 second. You might also note that now we have our messages augmented with these names. So we call our distributed nodes federates, and they're here indexed from 0. So federate 0 will be the message generator, and federate 1 will be the print message. You might also notice that the semantics of lingua franca are still preserved, even though we're running completely 2 different processes. And the way that it's preserved by default is using a coordination mechanism loosely based on high-level architecture, or HLA. And what will happen is that a 3rd process that is not shown here will be created for this federation, called an RTI, runtime infrastructure, from HLA, which will be in charge of coordinating the semantics of lingua franca between these 2 reactors. However, that those of you who are familiar with HLA might realize that that's very conservative. First of all your messages will now have to go through that coordinator, through the RTI. Second of all, these 2 reactors need to be in constant communication with the RTI to be able to coordinate and correctly execute. We do have a less conservative central coordination mechanism, which you can use by using this target property. So you can set coordination to decentralized. And once you do that, we will still take care of the communication ourselves. So all you need to do is in your message generator, just like an ordinary lingua franca program, you just will set a value to a port, and we'll take care of transferring that message to its destination. However, we'll no longer take care of the coordination. Instead, you would need to use an alternative coordination mechanism, which the one that we're using is, in this example, is loosely based on Tides and Google Spanner, in which you make some assumptions about the network delay and clock synchronization error and execution times, and you define what's called an STP offset, or save to process offset, which will offset the execution time, in this case of this print message, long enough so that it can receive messages from the message generator. Okay, so if I execute this, so hello world decentralized STP. So even though the RTI is no longer in the way, I can see that my source and destination are still honoring the semantics of lingua franca, meaning that the receiver is receiving the message at the exact same logical time as the source. However, if this STP offset wasn't large enough, so let me reduce it to 1 millisecond to cover the overhead involved with this communication. Did I do that correctly? I don't seem to be getting the warning, so let me. Maybe 1 second is still large enough. Yes, so let me just do it 1 microsecond, just to make sure. Yes, so 1 microsecond is obviously not enough to cover the overhead of communication and execution. So now you can see that we automatically have detected that the semantics of lingua franca was not honored. And you can do that in your lingua franca program by simply using this special syntax, which is an STP handler. And if you detect that the semantics of lingua franca in this case is broken, we'll invoke this STP handler, which will just print that this message is tardy. And it will tell you what the intended tag of the message was and what the tag is that it's trying to execute. And yes, so with that, back to Edward.
Thank you, Soroush. So you can imagine being able to use this for genuinely distributed applications, and that's one of our principal objectives. So the program shows now a 5-minute Q&A, so I will pause the recording. Okay, so for the next segment, we're going to talk about a few of the research projects that have been simulated, and I'd like to turn it over to Marten Lohstroh, a postdoc at Berkeley, who will be taking over as the master of ceremonies and giving me a break. Thank you, Marten.
Excellent, thank you, Edward. I'm sure you're happy to take a break. Okay, so let me share this slide. So as I was doing my PhD as a graduate student, coinciding with, I guess, the first year of this project, I spent most of my time trying to convince myself that the reactor model made sense, and then I spent a lot of time trying to convince others that it made sense. And it's a little difficult to do that without having actually built any artifacts, haven't done any engineering, without any proof of concept. So we started building things, and as more people bought into the idea, we got a much larger group of people that has been growing ever since, that have been actively contributing to this project. And at this point, it's actually become kind of overwhelming how much activity there is. So I just sat down and tried to kind of create a map of all the things that are currently going on in the project. And we won't be able to discuss them all during this session. But I would like to highlight some of them. So obviously there's a lot of engineering that goes into the compiler, and we have found that the research problems kind of find you as soon as you start building things. There's also been a very perhaps surprising synergy with the theoretical aspect of this work, where some of the primitives that we built into the language and that are key in the reactor model have been instrumental in developing some new theory. Specifically, it's allowed us to generalize and quantify the famous cap theorem that's due to Eric Brewer. That's some very recent work. We have also a lot of activity, keeping up with features that we want to see implemented in our runtimes, right? So each target language has its own runtime, and there are people actively working on those, keeping them in compliance, and that's a huge engineering effort. One recent thing that I think is interesting mentioning is, now that we have a federated execution capability and we have this way of reasoning about trade-offs between availability and consistency, it will be interesting to conduct experiments where we essentially do chaos engineering on our running programs to validate some of those ideas. Also, tooling, super important. I'm just very thankful that we were able to pull off, having a working IDE just a few hours before we had this tutorial. It's a lot of work that goes into this, and I'm very thankful for all the support from everyone on the team in getting this ready. Exciting new developments. Support for other editors than our Epoch IDE. I think that that will really be important in engaging more people in the community. We haven't talked that much about applications. Some of the talks in this session will compensate for that. And lastly, platforms. Well, since we now have a programming language that has time in it as a first-class citizen, it provides a whole new view on how to deal with real-time problems, specifically with hardware support that is much better at fulfilling what programs with timing constraints in them demand of the hardware. So that's also an interesting topic that we'll discuss. So we won't get into all of these, but the ones that are highlighted here we'll get to discuss during this this session. So because we won't get to everything and everyone, I would want to briefly highlight the folks that are involved in this effort, some of whom you've already heard. They spoke during this tutorial, other ones you haven't heard of. Recent collaboration with Julien De Antoni from INRIA has been very interesting, where we've been trying to focus on expanding tooling in the IDE, supported by a formal framework that he developed. We've seen the diagrams. That has been a huge feature for us. And Reinhard from Hangsleiden's group has been on this, and Alexander Schulz-Rosengarten has been the key developer behind it. Soroush, who has been featured in several of our segments during this tutorial, has been a very, very active developer and involved in several different research directions. And then TU Dresden folks have been really instrumental in all the work that we do in our compiler. I also wanted to mention Marten and his, I think, PhD student, Søren, who helped us get Lingua Franca working on a bare iron platform called Patmos. Okay, so I would like to introduce to you now Christian Menard, who has already been featured in several of our segments, who is at TU Dresden, and he will talk a little bit about an effort that he led in achieving determinism in AutoSAR. So I'll stop sharing. Christian, take it away.
Yeah, all right. So This is actually about not so much about ongoing research, but mostly about past research, and actually the research I did, and that brought me to that group and to the team, and to get hooked to Lingua Franca. So I looked into AutoZero, and for those that don't know AutoZero, so it's a worldwide consortium, an industry consortium, and it defines a standard. And they aim at creating a unified software for automotive applications. And this comes in two flavors. There's the so-called classic platform, which is focused on real-time applications, very constrained hardware, like small ECUs, microcontrollers, basically. And there's the newer adaptive platform, which is focused on very computational intensive applications. So high-level algorithms, autonomous driving, computer vision, these kind of things. And so this focuses on the adaptive platform. And the adaptive platform basically implements a service-oriented architecture. So you can define services, and clients can request these services, and then magically the two find each other via these middlewares. A common one is some IP. So all this communication is nicely hidden away. As a client, you just say, well, I want to talk to a server that provides the service, and then you can invoke methods on the service or subscribe to events of that service. Now, this brings some problems, actually. So service-oriented architectures are inherently non-deterministic. And to illustrate that, actually, we created a simple example. So this is a bit simplified, but this is most of the client code here. And what this does is, well, first of all, it requests a proxy to the service, so it connects to it and can send then stuff to the service. And what it does is just set the value, basically initialize the state of the service to 1, add a value of 2, and then retrieve the result. Nothing very complicated. Now, obviously, we would expect the result of this program to be 3, but it isn't, because AutoZero doesn't make any guarantees about the order in which these method calls are processed. They're actually all processed asynchronously. They might be processed in any order, and what we get is a distribution of possible results. So 3 is still quite likely, but it's only at 40%. And depending on the precise order in which events executed, or these methods executed, you might get any results. Now you could say, well, this program is obviously broken because it doesn't synchronize. Probably yes, we could use some mechanisms AutoZero provides to build in synchronization, to wait for the result, for the call to complete before invoking the next call. And yeah, we can fix the program in that way. But basically our argument here is that this becomes very tedious, and it's really, really easy to make mistakes for larger, bigger programs. And actually, this is nicely illustrated by the adaptive platform demonstrator that shipped alongside like the AutoZero distribution. So this demonstrator implements an emergency brake assistant. It consists of a few components. So there's a video provider, like let's say a camera, and then there's a preprocessor that does some filtering on the data and actually detects the lane already. So it sees where's the lane and which lane we're driving on. And then there's a computer vision component that sees what kind of obstacles are there and decides whether they are on the lane or not. And this then basically sends a list of the obstacles to the emergency brake assistant that makes a decision, is there a situation where I need to brake or not? Now, obviously, we want this to work correctly, and we don't want any weird timing errors in this kind of program because it's really, really critical. Well, there are plenty of those timing errors in this demonstrator, actually, as we found. So I don't want to go into the details of the precise nature of these errors right now. Just to give you an idea, this is an experiment I did where I run this demonstrator 20 times after one another, and I just measured how often these different kind of errors occur. And interestingly, for some of those runs, everything is more or less fine, barely any errors, but there are a few occasions where it's really above 20% of errors. And that's quite interesting because apparently not only is this program non-deterministic and has errors, also the error rate is non-deterministic, and it really depends on how all these different components come up and the timing of those. Now, in order to fix this, what we did is introduce a framework that basically is intended to bring vectors, the vector model to adaptive AutoSAR. And as I said earlier, this happened before Lingua Franca, before we got into the project. But this is basically using a standalone vector library. And yeah, the basic idea was to just grab the logic of each of the different components, interactors, and then have some transaction going on. I'm also not going into the details of this, that uses the AutoSAR utilities to still send messages back and forth. And yeah, so what's left for ongoing research in this is actually to integrate this back now with Lingua Franca. And what I would like to do is to be able to generate AutoSAR compatible code directly out of Lingua Franca programs. And it would also be interesting to integrate that with other automotive frameworks like ROS and AutoWare, which I believe you'll hear about in the next talk. So that's it for me.
All right, thank you, Christian. So even though Christian and I have been working closely together since 2019, the funny thing is that we actually still haven't met physically. One time I came very close. I was on my way to a conference in France, and actually we both were, but that conference got canceled. And I spent literally 3 hours in the Charles de Gaulle airport after I had to return because otherwise I wouldn't be able to get back into the country. We're still looking forward to that meeting. So the next person that I'm introducing is Soroush Bateni. I had the pleasure of actually meeting him this summer. He visited Berkeley. We've been working with Soroush since 2020, well over a year, and it was a pleasure to finally hang out and work together on this AutoWare project that he will present now.
Thank you, Martin. Okay, so I will just use the 10 minutes that I have to briefly discuss an overview of automotive related research that I've been involved with. And just as a precursor, I want to give a motivation behind that research, which is an observation that modern automotive systems are becoming increasingly reliant on sophisticated distributed architectures. They make use of AI, parallelism, and accelerators such as GPU. But more importantly, as an overall theme, all modern autonomous driving systems will benefit from two key properties. So one of them is testability, and the other would be that these systems should at all times have a consistent view of the state of their environment. And to just give a little bit of a more in-depth definition for what I mean by testability and this consistency, the testability, the way we define it is given an initial state and a set of inputs, there can only be one correct behavior. Now, the way you define behavior is really model dependent, application dependent. In this specific case, what I mean is that if you present a system with a test vector, you will always get the same output no matter how many times you execute your program. This is, of course, not exhaustive. You can't produce all the possible test vectors, but it is nonetheless a method that is heavily relied upon in the industry. The other would be that these systems should always have a consistent global view of the environment, which means that all the components should at all times be in agreement about not only the state of the environment, but how we got there, right? The order in which states has been changed in the environment that got us to our current state. And then if you have that, then detecting race conditions and causality loops and so on are very easy. And you saw sneak peeks of this using our tooling in earlier demos. So I have here two examples that we've used in our research extensively. One of them is AutoWare Auto, which is the second version of AutoWare. They, back in April, had their 1.0 release, which was an autonomous valet parking. You can see here. So you can essentially, this is running a simulator, although they've also demonstrated it using a real vehicle. This is the LG SVL simulator, by the way. You can see that in this demo, we can drop the vehicle at any point in the parking lot and then point it to a drop-off zone, and the vehicle is capable of driving itself and parking there. Okay, so we took this example and we looked at the architecture of it, which is quite complex. And then we asked ourselves those two same questions. Is this architecture testable? And does it always present a consistent view of the environment? So I won't go into details about all of these individual nodes. I just want to focus on two very simple, relatively simple nodes. So here I have the LGSVL interface, which is the interface node to the vehicle, and the behavior planner, which is generally the brain of the operation. The behavior planner is the one that tells the vehicle overall where to go. So it assigns trajectory. And you can see that the interaction that I'm showing here is that the LGSVL sends two things to the behavior planner. One is the state report, which reports the state of the gear, including also other things. But the main thing that I want you to focus on is that this state report contains the gear information. So is the vehicle in forward gear or in reverse gear? And then it also sends a vehicle kinematic state, which is the reports include, among other things, reports the velocity of the vehicle. Okay, so is this architecture testable? So in order to understand the answer to that question, we have to look at the underlying framework, which is in this case, Robot Operating System version 2. And what guarantees does ROS actually provide? In this case, it only provides the following guarantee. So you have point-to-point in-order delivery of messages. And you can demonstrate that by running a simple test. So imagine that the LGSVL interface produces a forward gear on the state report, and then later on produces a reverse gear, again on the state report. So what would the behavior planner see? Because of the guarantees provided in ROS, the behavior planner will also always see that the vehicle has been in forward gear, and then later it has switched to a reverse gear. So in that case, the system is both testable and presents a consistent view of the gear, because the behavior planner will always be in agreement with the LGSVL interface in the order in which gear changes has occurred. So both of them will agree that the vehicle has been in forward gear and then later has switched to a reverse gear. Okay, so in this case, ROS provides both testability and consistency. However, let's look at a more sophisticated test. And this test is as follows. So the LGSVL interface produces a state report, which contains the forward gear. Then it will produce a kinematic state. Because the vehicle is in forward gear, it will have a positive velocity. Then it will produce a reverse gear. And because then the vehicle is in reverse, it will produce a kinematic state with negative velocity. Okay, and now what does the behavior planner see? So the expected thing that it would see is it would see them all in order. So it would see that the vehicle has been in forward gear with a positive velocity, and then later it has changed to a reverse gear with negative velocity. However, what we actually see is when we ran this test for 300,000 times with varying periods of running this test, we saw that, and this is the important thing, among 300,000 tests, only about 0.2% of the time we saw that the behavior planner is not seeing the behavior as expected. So this is quite dangerous, because if you run this test even 100,000 times, you will not see any errors. So then you can come away thinking that your system is testable. And you can think that the behavior planner will always consistently understand what's going on with the vehicle. However, if you run it for 300,000 times, you will see a dangerous sequence like this, which is, so steps 1 and 2 has been seen by the behavior planner. So at the step 2, the behavior planner would think that the vehicle is in forward gear and it has a positive velocity, but then it sees 4. So now it sees that the vehicle has a negative velocity without being in the reverse gear, right? So how would the behavior planner interpret this? Is this because of an accident, that the vehicle has been impacted so hard that it's now moving backwards? Is it because of a component failure, or is it just because ROS has introduced an error? And the behavior planner really has no way of knowing this. And we have quite a few examples of this. I just included the simplest one. But the bottom line is, what we ended up doing was we actually ported this Auto 1.0 completely to Lingua Franca. You can see it here. And it interacts with the LGS-VL interface, although this is still a work in progress. There are some aspects of it that still require debugging, but we have extensive results that show that this port has been effective. So just to demonstrate one is, so the overall takeaways has been that this port of Lingua Franca using the centralized coordinator will have 0 errors, essentially. So the error rate will go down to 0. However, there is a drawback with our centralized coordinator, which is that because it's loosely based on HLA, a simple network partitioning will just stall the execution. For our decentralized coordination, we have a more interesting trade-off, which is that the safe-to-process offset that we talked about in the tutorial, you can actually play with it and change it. And you can see in this graph that the maximum theoretical STP offset for the example that we just saw is 24 seconds, which is too high. However, if you set your STP offset lower, the strength of Lingua Franca is that if that STP offset is violated, then you can detect that, whereas you can't detect that in ROS. So if your messages are late, as we saw in the tutorial, your STP handler will be invoked, and then you can handle that error. The other thing that I want to demonstrate is another automotive related application. This was raised by our industry partner, Ravi Aktela. And this was about an intelligent intersection where you can see that there are 4 vehicles here that want to enter this intersection, and they need to coordinate so that they don't have an accident, to put it bluntly. And really, there are 2 ways of coordinating this. One is you can have a roadside unit that coordinates their entrance. That's not as easy as it sounds, but the more complicated solution would be to have these vehicles coordinate in a P2P fashion, and that is also ongoing research. But the thing that I want to show is that we actually implemented this intelligent intersection using another prominent vehicle simulator, Carla. You can see the demo here. So the structure of the demo, that in this case, you have 4 vehicles, and which represent the vehicle controllers and so on. We have a roadside unit, and we have our Carla interface, which in a real application would be replaced with an actual vehicle interface, just like Ottawa. And we actually have a demo of this on YouTube with, it's not switching to the, okay. So you can actually try this. This is on our Lingua Franca repo. It's called Carla_intersection.lf. It's under experimental. And you can see that I'm just running the generated Py file, which will in turn run this. And if you have Carla installed, you can play with this. You can change the vehicle controllers, the RSU, and so on. And you can see that the vehicles are coordinating their entrance to the intersection. And there are a lot of interesting trade-offs involved here, but I guess we don't have time to go over them. But feel free to refer to the quantifying cap paper that Marten pointed to. And with that, back to Marten.
Thank you, Soroush. This is really extremely cool work, and I'm really looking forward to see Lingua Franca have an impact in the automotive community. So after Soroush, the next person I will be introducing is Efsane Soyer. She is a junior in computer science at Berkeley, and she did a terrific job presenting her work in progress that she has been doing together with Shaokai Lin, one of our graduate students, at the recent NSF CPI CPS PI meeting, and she will present part of that presentation right now. Efsane, take it away.
Thanks, Marten. Let me share my screen. I guess you can now see my screen. Okay, perfect. Hello, everyone. So we also want to include the notion of time, we kind of talking about it at every layer of abstraction instead of hiding that from the designer. So we're proposing an engineering paradigm where timing semantics is baked into every layer of abstraction, from the microarchitectures to the model of computation. And at the level of microarchitecture, we propose combining Lingua Franca with PRED machines, which are processor architectures that are capable of precise timing. So our goal in the PRED project is to demonstrate that you can achieve excellent performance while still having control over timing at the microarchitecture level. And we have demonstrated that timing predictability and repeatability can exist in parallel with performance. Like as of now, 3 generations of PRED machines have been developed, and FlexPRED, the latest version of the PRED machines, is a fine-grained multi-threaded RISC-V processor designed specifically for mixed criticality for real-time embedded systems. So in other words, FlexPRED offers a configurable architecture that can handle both real-time functions with repeatable timing and non-real-time but performance-sensitive applications. So we are currently working on bridging the gap between Lingua Franca, the deterministic programming model, and the PRED machines, the processor architecture that are timing predictable and repeatable. And in order to make these timing-aware layers of abstraction work, we are making progress towards running Lingua Franca on FlexPRED architecture. On top of that, as you all know, embedded system constitutes a major part of CPS applications, and we are working on adapting LF on various other embedded platforms as well. We are currently supporting Rocket Core and Spike platforms and developing the Arduino this semester along with the PRESPRED. So right now, I would like to show you a quick demo and some additional supports that are needed to support this bare iron platform. So here we have, sorry, I'm really bad at typing and speaking at the same time. So here we have an LF program for a robot that has sensors, a controller, and motors. So we have been saying how we can run this program in various platforms, but how can we actually run them? What supports do we need if we want to run it on a bare iron platform? So if we go into So one argument that we have been talking about is the idea of the physical time. And normally the way we support this is using the OS features, OS tools. However, in a bare iron platform, we kind of need to get the current physical time by another methodology. And the way we implemented it is that, like, by counting the cycles, we are getting the notion of this physical time. So this is one of the additional supports that we give here. And the other one is this return, this custom return function in order to terminate this spike simulator. And lastly, we have this SBRK implementation here to enable memory allocation in bare iron platforms. The one thing that is worth emphasizing here is that just by implementing couple extra services, we were able to make LF runtime works in a bare iron environment. And like, run this program now. Here. If we run this program, we see that the program terminates with an emergency stop because the deadline is missed. And this is because we have a deadline specified in our LF program for both our controllers and sensors, and which is a really good practice when it comes to real-time systems. But since Spike is not an actual architecture, we kind of make assumptions here before we run, including the assumption for clock frequency of the Spike. And when the clock frequency and the deadline value, they both determine whether or not we are missing this deadline. So if we want to avoid missing this deadline, we either need to increase the value of our deadline, which is not always possible depending on the application, or increase the assumed clock frequency. So I guess that would conclude my presentation. Thank you.
Cool. Thank you, Efsane. This is excellent work. I always like to think of this project as kind of a moonshot project that is turtles all the way down, so to speak, where we have time at the programming level and all the way down to the logic. Really nice. Okay, going to the next speaker, Alexander Schulz-Rosengarten from Kiel University, who has already presented several segments in this tutorial. He brought to the table the idea to augment lingua franca with modal models, a new syntax, new diagrams, and this is a work in progress. I really see this as a really interesting cross-fertilization between lingua franca and the sequential state charts that his group is working on. All right, please go ahead.
Thank you, Marten. Yeah, most complicated systems usually work in some kind of mode. So they have different modes of operations. And the idea of modal models really is to express these modes in some high-level fashion. And usually this is done by some form of finite state machine or state charts dialect. And here for lingua franca, the idea is to create modal reactors, and they should not be too intrusive into the syntax. So they should come in as a lightweight layer on top of the current structure of reactors and reactions, and especially don't hinder the form of polyglot nature. This is essential to the lingua franca languages. And in order to fill the gap to the classical visualizations of state machines, here again the diagrams play an important role. And on my screen you can see an example This is inspired by the steam boiler specification problem by Jean-Raymond Abrial. The steam boiler here has a few sensors, computes the water level, and by that controls the boiler. And if I look into the water level here, you can see that the computation is depending on the mode of operation here. And if we look into the normal mode, you can see that there are two reactions in it, and that's essentially it. The modes encapsulate the contents of a reactor, and the code generation then will handle the activation and deactivation of these timers, reactions, and so on, so that only those in the active mode will be triggered and can run. And here in the normal mode, the water level is computed based on the sensor, and there's another reaction here that can actually switch the mode. So here in the effects, other modes are declared that allow us to draw these diagrams, and the actual mode switch is done in the target code, same as setting an output. This will change the mode of operation. And if the water sensor fails, it will switch to a rescue mode if there are flow sensors available. If these also fail, well, it has to enter the emergency mode and the entire plant needs to be shut down. And these modes can be composed differently. So if you look at another example, you can see here a reactor with two modes, one converting, one discarding. And in the conversion mode, you can see a converter that has uppercase and lowercase. And what this program does is it takes a string, character by character, and either discards characters or processes them by converting them to upper or lowercase. And I can quickly run it. And you can see this one switches between discarding characters, converting them to uppercase or keeping them lowercase. And what's maybe interesting here is we also have different ways of entering modes, because you can decide if you left the mode and then re-enter it, you can decide if it should continue as before or it should be reset. And in this case, it continues. So even after switching to lowercase and activating the discarding mode, when it re-enters converting, it will still convert to lowercase and will not switch back to the initial configuration of converting it to uppercase. And these give the opportunity to the modeler to express such modes in lingua franca programs, but also give new ways of performing static analysis or model checking on the program that involves the modes of operation. And these will be part of lingua franca in the future. Thank you.
All right, thank you, Alex. I think that this will be a very powerful extension of lingua franca. This is very neat. So next up is Shaokai Lin. I would like to briefly mention that so Shaokai is a second-year graduate student in our group, and at some point he asked, so could we maybe get some undergraduate students to work with us in the group? And I said, I don't know, how do we do that? And so he organized a recruiting effort, and that has led to about a dozen undergraduate students being now engaged in work related to lingua franca. And he's been helping advise many of these groups. And now he will talk about his own research, which is automated verification. He's interested in verifying safety properties of lingua franca programs. Shaokai, please take it away.
Okay, thank you very much, Martin, for the very kind introduction. So hello, everybody. I'm very excited to present the current work on leveraging formal methods to verify lingua franca programs. So cyber-physical systems tend to be safety critical, and often we don't just want to rely on testing, but also want to obtain formal guarantees about the correctness of the system. So in this demo, I'm going to show you how we can leverage the semantics of lingua franca and the current state-of-the-art SMT solvers to automatically verify some of the safety properties that developers might have when they build their system. So, so right now, are you able to see my intersection example?
Yes.
Okay. So what you see here is a implementation of the centralized intersection application. This is similar to the prior demo that's shown by Soroush, where connected vehicles try to enter the intersection autonomously without human intervention. And here you can see that the intersection is being managed by this RSU reactor, which stands for roadside unit. And there are currently 2 vehicles here communicating with the roadside unit. And the roadside unit essentially directs the vehicles and tell them, which one to enter this time, which one, to wait for a minute and then enter in the future. And what we're interested in, for this application is to see whether the behavior of this particular program allows for scenarios that are potentially dangerous. For example, could this program possibly allow for the scenario where both vehicles simultaneously occupy the same intersection, in which a potential collision could result? So let's try to check that using SMT. So here I have encoded the semantics of the lingua franca program, the application of the intersection, as well as the safety property, which is the mutual exclusion property, into a formal modeling language called Euclid 5. And here you can see that using Euclid 5 language, we have modeled the timing semantics in lingua franca. We're also modeling the reactions and the connectivity information in the intersection application. We have modeled the semantics of a trace, modeled the semantics of the happen before relation in reactors. And we further modeled the topology of the application, as well as what individual LF language component means formally. And lastly, here is where we detail all the semantics of the reactors. For example, events must be time-stamped, and then they are processed in timestamp order, etc. And all of these are written in first order logic. And so here we construct our safety property. In this case, it's mutual exclusion. It is originally written in linear temporal logic, and here we transpile the LTL property into first order logic property. And then when we run our program using the Euclid 5 toolchain, we get an output like this. And you can see that the SMT solver has successfully found a counterexample that will lead to this particular unsafe scenario where 2 cars occupy the intersection at the same time. And the idea here is that the developer can manually go through the trace and try to recreate the behavior of the lingua franca program, and this can help them identify the potential bug in the program. And this will be an iterative process. when the solver no longer finds a trace that can lead to this scenario, we would say that this program is safe and basically satisfies satisfies the mutual exclusion property. Okay, so this is the current status of the automated verification effort. We are currently working on automatically generate this formal model, formal Euclid model directly from lingua franca programs, because most of the information can in fact be derived from the coordination layer alone. We actually don't even need to look into the target code. So this will also be a target independent feature. And we're also working on making the proofs compositional so that we'll be able to construct proofs incrementally for larger systems. Okay, thank you very much for your attention. And this concludes my demo.
Very cool. Thank you, Shaokai. I should also mention that it shouldn't come as a surprise that Shaokai is our formal verification guy, since he's also co-advised by Sanjit Seshia. Up next is Hokeun Kim. Hokeun used to be a fellow graduate student. We were both graduate students in the same group, with Edward being our advisor. He moved into industry. He worked for Google for a number of years, and he was very recently hired as a professor at Hanyang University. Hokeun has recently gotten involved into several sub-projects. He's been helping out with the federated execution in the TypeScript target, and he actually rewrote the code generator in Kotlin, our TypeScript code generator in Kotlin. So he hit the ground running. His focus of his PhD work was on security, and we're very much interested in leveraging his knowledge about security. So he will talk a little bit about what he plans to do in the context of lingua franca when it comes to security. Hokeun, please go ahead.
Thank you, Martin, for the kind introduction. I'll be discussing ongoing research on how to secure communication for federated execution in lingua franca. Currently, in lingua franca, we assume that the RTI, the runtime infrastructure, and all federates run under a trusted environment without any adversaries. Thus, all network messages are sent in plain text without any protection, such as message authentication or encryption. However, this becomes a considerable challenge when this assumption is not true. For example, when we run LF federation communicating over the internet or on an open network. In such cases, the federation will be vulnerable to various attacks, including maliciously altered messages that can run malware on federates when they are deserialized, or sensitive information being leaked to attackers. Here's an example attack scenario where the attacker joins a federation with a malicious federate. The RTI authenticates each federate using a unique identifier called federation ID, which is also sent in plain text. The attacker can simply eavesdrop on the federation ID and present it to the RTI to join the federation in place of a valid federate, as shown here. One may think we can apply conventional security solutions such as SSL TLS or Kerberos to address this problem. These conventional solutions have been widely used and very successful for the web. However, they require digital certificates or standard security measures, which may not be a proper option for resource-constrained devices. Challenges arise when we try to apply these solutions to lingua franca's federated execution. This is because not all federates can afford the security overhead due to the additional network payload or heavy computation. And the distribution of secrets is a non-trivial problem since there is no established way of building trust among these devices. Also, the support for the distributed communication is limited for these solutions. To address these challenges in securing communication for the LF Federation, we are using SST, Secure Swarm Toolkit, an open source software toolkit for authentication and authorization of the IoT using edge computing. This is also my PhD thesis work. And the main component of SST is called auth. Auth is a locally centralized, globally distributed software entity for key distribution for security services such as authentication and authorization. SST provides knobs to configure options between stronger security guarantees and less overhead, including communication or computation overhead and energy consumption. Therefore, SST can provide security solutions for federates that cannot afford conventional security measures. A remaining challenge would be how to find optimal configurations for given applications and platforms running the LF Federation. The work in progress design of integrating SST with federated LF is as follows. The auth plays a role as a key distribution center among the RTI and federates in Lingua Franca. The security configurations are going to be generated as part of the code generation and distribution of an LF federation. These code generation and distribution processes will include the initial setup of SST and the auth, specifically the key distribution mechanisms, communication policies, and secret keys. We are currently focusing on the centralized execution of LF as it is more aligned with the SST's architecture, but we believe that this can be easily extended to the decentralized execution. Okay, this ends my presentation. Thank you, and back to Marten.
All right, thank you, Hokeun. SST seems like a really perfect fit for Lingua Franca, since Lingua Franca targets both small embedded systems for which that resource consumption versus security trade-off is really important, but also large-scale distributed systems. So yeah, this looks very promising. Okay, last but not least, I would like to introduce Peter Donovan. Peter Donovan is one of the undergraduate students that we recruited earlier this summer. Peter is a rising sophomore, and I've been really impressed with his work. He has basically single-handedly built a Visual Studio Code extension with lots of features built on top of the language server that gets generated as part of our compilation process that Xtext provides. And so there is already a basic version that we will probably publish soon based on this work, and that would bring really nice Lingua Franca features to the VS Code editor. So Peter, please go ahead.
So the nice thing about using the language server is that it allows us to use the language server protocol, which is a standard for communications over JSON RPC between the language server and the editor. And so that allows one language server to be reused across many different editors that also follow the protocol with very little additional code. Right now, we're working on compatibility with VS Code, but of course, we would like to support your favorite text editor, whatever that is, and hope that it will allow a lot of code reuse. So the editor sends information about Lingua Franca source files to the LF language server, which is a jar, and the language server does Lingua Franca syntax validation, and it does any analyses that the user requests, and it also can use the generated source code as input to target language tooling that, like, you might be familiar with, like formatters and linters, And then it sends the results of lingua franca specific analyses and target language specific analyses both back to the editor as appropriate. So here's yes. Okay, so here's the smokers example that Christian mentioned earlier. The example of a program that is implemented a lot more elegantly, that really benefits from the lingua franca syntax. So as you can see, diagrams are available in VS Code because of this extension as a result of Alexander's work. The language extension also obviously detects lingua franca syntax errors. So here it reports that I inserted a typo and now the main reactor doesn't have a name that matches the file name. And it also validates it validates target language code. So if I insert a syntax error into this reaction body, then there's a little bit more of a delay. There are certain optimizations in the code generator that haven't been implemented yet, like it doesn't cache previously generated models in its correspondence with the generated code, but it does report a meaningful error message and in the right place for the user. Of course, the language extension or the language server also provides the same basic features that are available in Epic IDE, such as go-to references. Okay, that concludes the extension.
All right, perfect. Thank you, Peter. Yes, this VS Code plugin I think will be quite instrumental in getting a broader community engagement. It's not just a language server, it's a language and diagram server, as it's currently called in our code base. And Alexander Schulz-Rosengarten and several of his colleagues have worked hard to get the diagram part working, which we're also very thankful for, that's now available in VS Code, because without it, that would really have crippled the user experience. All right, with that, I will hand it back over to Edward for concluding remarks.
Okay, great. I would like to start my concluding remarks with just, I forgot to show a graphic relating logical time and physical time that might be useful to kind of recap some of the core concepts in lingua franca. So this is a description of how the reflex game program actually operates. So one thing that maybe isn't immediately obvious is that when a lingua franca program starts up, there is a best effort alignment of logical time and physical time. That is, what happens is that the logical time gets assigned by requesting the physical time from the platform. In a federated execution, there's a stage of coordinating these logical times and synchronizing and creating a clock synchronization layer. This was built by Soroush Bateni, and so that all of the federates agree on the current starting logical time, and to the best extent that they can, they synchronize their physical start times as well. So in the reflex game example, at that logical start time, there's a startup event and reactions execute logically instantaneously.
Edward, did you mean to share your screen?
Oh, I did. And I'm looking at it myself, and you guys can't see it unless I share it, can you? I once gave a whole talk like that. And interestingly enough, people thought it was a really good talk. I was looking at my slides and nobody else was seeing them. And somehow it worked out. But in this case, the graphic really does matter. So apologies. Yeah, so this is,
Yeah, we can see it.
thank you, Martin, for correcting it. So at the startup time, you get this alignment of logical time and physical time, and reactions execute logically instantaneously. And if you recall in the reflex game, they'll start a listening thread which listens for keyboard input, and they print a welcome message, and then they schedule an action, a logical action with a random delay. So that's a forward-looking thing on the logical timeline. And then when that executes, there is again a best effort alignment. You can never make these alignments perfect, but the Lingua Franca runtime tries to align that logical time with physical time, and it records the logical time and prints a prompt in a logically instantaneous reaction. And then it waits for user input. And when the user hits a key on the keyboard, the physical time at which that occurs is used to assign a logical time via this construct in Lingua Franca called a physical action. So that logical time then triggers reactions that occur at that logical time, which then print the response time. And at that point, this also then schedules another random delay. And if the user hits a key press before the next prompt gets generated, again, a physical action will occur. A logical time will be assigned. That logical time will be detected by the program as being too early. So the program will detect that the user tried to cheat and will request a stop of execution. Okay, so I forgot to show that earlier, and hopefully it is helpful. But what I'd like to do now is just conclude with, I think, what is hopefully obvious for those of you who have been persistent enough to stick through all of this. This is an incredibly exciting project with a lot of potential and an extremely talented group of people that I am just thrilled to work with. I, like Martin, am looking forward to meeting some of them physically in person. It's kind of remarkable how this pandemic has led us to actually work very closely with people for years now without ever having physically met. It's a very curious situation that I've never experienced before in my life. But in any case, I'm really enjoying working with this team. And with that, I will stop the recording and hang around for any questions that might come up.